Do we have our guest here?
Yeah.
Okay.
We're now live on the world stage.
All right. Well, let's start off with introductions so everybody knows who's who.
Let me run over a couple of required things first. Legal notification that this meeting is being recorded and will be hosted on the Internet Site YouTube channel. Hope I didn't bumble that too badly. There is a new sign-in sheet by Patrick yet again. I will need you to sign in on that, even if you signed into the morning version. If you're attending by team, we'd appreciate if you enter your name and affiliation into chat. We have several people attending online today, more than in the room, so be sure to direct your conversations towards the middle of the room wherever possible. The owls are how they see and hear us. And just know that if you're whispering, they may also hear that. All right, and with that, I think we're ready for introductions.
Go ahead.
Okay, I will start. My name is Josh Patnod. I support the ad facilitation team. We're going to go this way.
Jim Doherty, Oregon Hanford Cleanup Board.
Bob Quirk, member of the public, not a member of the House. Rob Davis, I represent the city of Pasco and I'm the chair of the Tank Waste Committee, or excuse me, the TWST Committee.
Chris Sutton, local environmental interests, and I'm vice chair of the TWST,
It's hard to
or whatever we call it now.
Laura Caulfield, Cat Mine supports the DOE. Medium Trip, DOE, and DVFL for HAP. Pauline Drinkard with HMIS, supporting DOE.
Jim Alzheimer, Patrick Conrad, HMIS. Matt Osmondson, PNL.
Kathy Dubois, non-management, non-union.
Ryan Miller representing ecology for the HAP.
Junior Florence, HAP excavation.
I'll run down the teams list and give you all an opportunity to open your microphone and introduce yourselves. We'll begin with MBK.
Ambika Chakrabarty, this is ecology.
Kevin Danby representing Franklin and Grant counties.
Dan Solich, member of the public.
Dana,
Hello, Dana Cowley, HMIS.
Matt Henderson,
Hi, Matt Hendrickson, Oregon Department of Energy.
Larry,
Larry Brandt, member of HAB, not a member of this committee.
Jane,
Jane LePage, Department of Health.
Matt Lynch,
Matt Lynch, Nez Perce Tribe.
Matthew Campbell,
Matthew Campbell, CTUIR alternate.
Dan McDonald,
Dan McDonald with ecology.
Dana,
Dana McFadden with ecology.
Mia,
Hi all, Mia Burke, Hanford Challenge.
Steve,
Steve Needles with ecology.
Eric,
Eric Pierce with ecology.
Rob Sarmley,
Rob Parmalee, non-union, non-management.
Jennifer,
Jennifer Roberts with H2C.
Simone,
Simone Anter, Columbia River Keeper alternate.
Susan,
Susan Coleman, public at large.
and Michael.
Michael Turner with HMIS Tri-Party Agreement.
Thank you, everyone. Everyone mail on the room and online. Back to you, Rob.
Well, welcome, everybody. And Matt, thanks for showing up. We've been trying to get this for about 2 years now. We've had an action to either develop some advice that would lay down our values for grout or grout stabilization of the processed liquid waste. And so we've been been looking forward to this for a while. By the number of people that are online are also very interested. So, and recognizing you're an expert in this field and have published many papers in the area. So we're anxious to hear the latest approaches on grout and mobilization for waste.
Comes up to it. And I'll just say if there's anything in the presentation that I won't touch on you guys are interested in, I'm always happy to come back or give follow-up questions. I think I'll try my best for the presentation to give an overarching thing, but I can sit here for 2 days and fill time with you guys. So.
Thank you. So what, can we just start the presentation?
Yeah, you're right. Yeah. So am I sharing it from mine or are you doing like a public share or?
Yeah, we'll want to make sure we do a public share so everyone on the online can see as well.
Okay, do you want me to just do, say, next slide?
That'll work.
Okay.
Can we make it so we see the whole screen?
Get a little bigger.
And does the spike turn?
Here we go.
Thank you.
Okay, so I'll jump right in. Do we want to do, if anyone has questions during it, do you want to hold till the end or just do it as we go?
For continuity's sake, we'd like to hear your presentation.
Okay.
And then we'll go back and I guarantee you we'll cover almost every page.
Okay, great. No, all good. Okay, so yeah, so thanks everyone for the invite. This is my third time presenting to the HAB and the subcommittees. I don't think I've been in front of the group since 2019, maybe. My role at PNL, I lead our IDFPA program, which supports the Hanford mission in everything. My program does everything from fundamental take waste chemistry to supporting some regulatory support and everything in between. The majority of the team that works with me do the design, development, qualification, testing, and modeling of various waste forms, both glass, grout, and alternative, to meet all the treatment and disposal needs in the Hanford mission. So we have a really broad team of chemists, chemical engineers, environmental scientists who support this mission. So we've got a nice broad team underneath me. So some of the work that you'll see throughout to the day, not necessarily all me, but got a nice team at PNL who supports us. So the presentation I'm going to give today is one of my favorite ones that I like to give. I give this to universities, Hanford site contractors, academics, and then also new staff who come to PNL. I kind of see this as my table setting presentation of just getting across what I consider to be the fundamental information for everyone to sit down and have some intelligent conversations of what grout is, how we apply it, and how we test it. And like I said before, if there's anything that I don't cover in this, I'm happy to answer questions or come back and give more details, whatever. So I try to keep this within a nice 30 to 40 minute window. Okay, so if you go to the next slide. So what I'll try and do is build from the bottom up here, making some comparisons, give some understanding of what the fundamentals of cement and cementitious materials are and how that leads into how we apply this class of materials in nuclear waste management and disposal, and kind of get across some of the fundamental information, but also some of the key definitions of what we're talking about when we are speaking to applying grout in the Hanford mission, and then some of the properties that we would target and what dictates those properties and how we gain control over them. So first, if we just take a look at where we would normally apply cementitious materials, just broad usage, the most common one is we're trying to build something that has strength. Cement is one of the most consumed materials that we use globally, and the main reason for that is we use it to build things. It's a very simple, relatively simple and very well understood approach to make a material that can be give a lot of structural strength for a long period of time. That's why we use it so much in infrastructure. And here at the Hanford site, we've got many examples of that. We've got buildings and barriers constructed of concrete, just like we would in any infrastructure application. Next bullet. The next approach that people take is if you've got a large space and you want to fill that space with something solid and do some void filling, cementitious materials are again an excellent low cost low heat generating approach to fill empty spaces. This is done all across the globe, and specifically when it comes to waste cleanup, this is what we do when we D&D facilities, or if we need an urgent space filling. So like a perfect example of void filling was the Purex tunnel. To remediate the collapse that happened, you go in with the material that you can flow into that large space and fill the gap. The next bullet. So now we start to drift into things that applications that are more relevant to waste disposal, not just nuclear, but waste disposal in general. The other, another good use of cementitious materials is they can be used for stabilization. So if you have a loose or particulate material that's hard to handle and transport, using a cementitious material that starts as a liquid slurry type material and then solidifies into a nice solid mass that you can move is a great way to stabilize particulates. And this is used in the waste disposal community quite broadly when we require stabilization. And here at Hanford, where this would be applied, is handling the particulate secondary waste that will be generated from WTP. So things that come out of the off-gas management system, fine particulates, they'll need to be stabilized in order to be disposed of. And you would use a cementitious material or grout to do that. And next bullet. And the final one, where we drift more into the nuclear application space, is cementitious materials are great for solidification because fundamentally they take a set of dry reagents, mix it for hydraulic cements, mix it with water, and it turns that liquid into a solid. So when we're doing solidification or of a liquid waste, whether it's from a nuclear source or a wastewater, cementitious materials make a perfect requirement for this because you just add in some dry reagents and that liquid stream is now a solid mass that you can move to your desired location. And it also gives you control over the properties of that final solidified product, depending on where it's going for disposal. So those are the four main applications that we see generally across the globe for hydraulic cements. And we use them here at the Hanford Mission all across. So go to the next slide. So we'll get into how do they fundamentally work. So we use cement as the example here, but pretty much any of the reagents that we would use in forming a cementitious material go through a fairly similar process. And that is the hydration reactions. So I'm keeping this, there were some cement experts want to give this to cement classes. Got to be explicit here that these are, we're speaking to hydraulic cements here. So cements that react with water. We're not talking about materials that like putty you would put on your wall that react with CO2 in the air. Specific to hydraulic cements, what they do is they go through a series of reactions called hydration reactions. And that is how you go from taking a liquid mixed with the dry powder into a solid. So what happens is when you take cement in general, that fine powder, and you put it into water, the particles start to dissolve in the water. And as they start to dissolve, those individual grains start to dissolve, you release the dissolved components into solution. And one of the fundamental chemistry rules is as you start to increase concentrations in solution, you eventually hit some solubility limits. And as you hit those solubility limits, things start to precipitate and grow out of solution. You can only keep so much in that liquid environment. And that's exactly what's happening when you put cement into water. The individual grains start to dissolve out, concentrations rapidly increase because it's a very fine powder, high surface area, a lot of dissolution happening, and you start precipitating what are known as hydration products. And these hydration products, depending on what the chemical content of the liquid is and what the makeup of that cement powder is, can be a range of amorphous or crystalline phases that start to grow, they start to link up together, and that's where the material starts to get its strength from. And eventually you get to the point where you reacted enough of the water and precipitated enough of those hydration products that you form a solid mass. So that liquid goes into a slurry and then cures into a solid particle. So the design in the top right, it's not really, it's probably clear on the paper slides. That's showing an image of the progress of reacting cement grains over time. So those red pieces, those are actual fine cement particles, unreacted. And in the middle, once you've added it into water, the yellow are the hydration products that are starting to form as those grains start to be consumed. And then as time goes on, you see you get more of that yellow, those hydration products start to grow. Eventually the hydration products grow out, they link together with one another, and you end up with microstructures that look like the electron micrograph in the bottom right, where those flat areas are the cement grains, and all those needle crystal-like structures going in between, those are the hydration products. So as they grow out, they start to link together, the grains become locked in, and that's how you start to convert into a solid mass. One thing to take away from this slide is regardless of the application, whether it's a sidewalk at your house or another cementitious material, once they get to that hardened, cured state, they're not done reacting because you do have those unreacted grains that sit there. So cements are a dynamic system that continually react at a very, very slow rate, but over time they continue to evolve. And this, depending on how you engineer your material and what environment it's placed into, those continued reactions can lead to processes that could fail if you're not smart about where you're putting it, or like most of the cement industry does, material can get better and better with time. And the perfect example of that is the Roman concretes. Those are materials that were designed just to last for a few decades, but based on the knowledge they had at the time. But those materials, because of that continual environmental reactions, have actually become stronger and less porous over time because you get those unreacted grains that slowly continue to react. The hydration products themselves, they'll slowly evolve. So if you're smart with your design, you can make materials that are very long lasting and maintain the properties that you've engineered into it. So go to the next slide. We'll go into, I promise, only one slide of chemistry. I am a chemist in training, so I have to show this, and I keep a little bit of my core science in. So the main phases inside cement that are reacting are what drive the majority of the formation. There are other phases that do contribute to the hydration products, and depending on the additives you put in, this will vary. But this is just a nice slide I like people to kind of walk away from. So the two main reactive phases in cements are tricalcium silicate, which is halite, and dicalcium silicate, which is baelite, C3S and C2S. Cement researchers like to have their own notation. They can't just use nice chemistry notation. So the notation at the end, that C3S and C2S, those are the cement notations for the specific compounds. So when you take cement and you react a cement powder and you react it with water, the halite, the tricalcium silicate, is what reacts first. So the calcium and silicon within that phase, that's what starts to dissolve when it interacts with the water, and you start to precipitate calcium silicate hydrates, CSH, and that's the primary contributor to the resulting cement structure. So the halite, best way to remember it, it's the A team, it reacts first, and I pity the fool who forgets that. I gotta laugh. Oh, I gave this presentation to a university class earlier this year, and I said that joke, and it was silence. And I thought, it's not just the gray hairs, I am getting older.
It's no longer funny.
I know it's gone. But the halite's what reacts first, and then the baelite, the dicalcium silicate, the C2S, that's what reacts slower. So after a couple hours, the baelite starts to come in, and that's what gives the material its kind of late in life strength. So a lot of the heat that's generated comes from dissolution of the halite, rapid reaction, and the baelite reacts second, and that's when the material really starts to solidify. What you end up with are the CSH, which can also be CASH, CASH for calcium aluminosilicate, and then they can also be calcium, sodium, aluminosilicate hydrates, depending on the network and how level of detail you're going into. So that's the main network former. And another product of it is you make Portlandite or calcium hydroxide. That's what makes cements have a higher pH. And that high pH environment is what chemically stabilizes the CSH. So the two products that you make, one gives strength and one kind of acts as a protectant. Okay, so we go to the next slide. So what does the progression of a cementitious material look like from the time you make it through its entire life? And I'm lucky that cementitious materials follow a similar pathway and terminology to the career that Will Smith has had. So when they start out, you have raw materials, similar to how, if you were a fan of hip hop in the late 1980s, Smith and Jazzy Jeff, their original stuff, it's not bad. It's a little rough around the edges, but it's a raw material. Once you mix that cement powder with water, what you get is what's called a fresh material or fresh paste. Similar to Will Smith first thing being the Fresh Prince. Once you've had a fresh material, you're very much in a slurry state. And as those cement reactions start to continue and we grow some of those minerals and things start to link up, you end up with a hardened paste. And Will Smith became hardened in the mid-90s when he moved out of that Fresh Prince role, starred in Bad Boys in a very R-rated film that they should have stopped at just one. But you end up as a hardened material. And once you end up in a hardened material, in a short time after that, you are what's called set. And set is usually defined as when you've attained about 90-ish% of your strength, which depending on the mix could be a couple hours to a couple days, And for most materials, the industry standard, in 28 days, most materials will have achieved about 90% of their overall strength, and you have a set material. But at that point, it's still a young cement. So around 1997, how long ago that was, Will Smith was only 29 years old. He was still young, but he was set for life. So at that point, once the material is cured and set, you have a young cement that, because of those unreacted grains and interacting in the environment, it'll slowly evolve with time, and you end up with a mature cement that has slightly different properties, and depending on the service lifetimes in the environment, that will continue to mature over time. Now, we do have different reactions that occur. Okay, next slide. And sometimes maybe the cement will crack. Smith cracked a couple of years ago. But that also depends on what your material is, what the service environment is, what loads are put on it, and a lot of effort that goes into us on the waste form side, but also the cement and concrete industry, is trying to develop tools to be able to model and predict the probability of what the degree of cracking in cement materials would be, and what the failure modes would look like. Some of the certainties in life are death, taxes, and your concrete will crack at some point, but that cracking could take thousands of years depending on what you put into it. So next slide. Okay, so that was the case, just speaking solely to cement. But in nearly every application in waste immobilization or the general infrastructure application of cementitious materials, you don't just use 100% cement. And why is that? Why do we use additives and other things? There's a number of reasons for that. The first one is from an environmental standpoint. In order to produce cement for use in cementitious materials, you require a lot of heat. You have to take a clay material, heat it up to very high temperature to produce clinker. We'll touch on that in a second. That goes into your eventual cement powder. And doing that, it's usually done. We make a little bit of cement here in the US, but relative to the rest of the world, that cement generation is done with not carbon-friendly processes. So when we do environmental analyses, this is where you pay the largest carbon penalty, for example, if you do those type of analyses, is in the production of cement. So you get a lot of CO2 production because it is a byproduct of the process, and also a byproduct of most of the power sources that run our cement production throughout the globe. The other one is demand. Like I said, cement is one of the most consumed substances annually across the globe. So there's a large demand for cement. So if you can use other materials or waste materials and lessen your demand, well, you save a lot of material, and you also save a lot of cost. You'll see with a number of the other materials that I'll discuss that we use for cement or for waste forms and other cement applications, we look for materials that are wastes or byproducts of other industrial processes where you've already paid your energy penalty, you've already paid a cost penalty. And if you would take these waste materials that have similar properties and add them in, you get substantial cost savings. So that's a big push in industry, is anything you can do to reduce the amount of cement you use, the better, because your costs will go down 1-to-1. Okay, so go to the next slide. So some of the definitions that take it from cement to the actual materials, and I'll show this how this fits in the waste management in a second. So if we take cement and water and mix it together, that's not usually a material that's used quite a lot because of that cost factor. So what people try to do, especially in an infrastructure or a structural application, is you want to add stuff into it to take up space without sacrificing properties. And the two most common things you do is you either add in sand or you add in rocks. So if you take cement and water and you add in sand, that gets you a mortar. If you take cement, sand, add in some rocks to it, that gets you concrete. And in both of those cases, those aggregates are just acting as a filler. They're not really giving a lot of properties. You might get a small uptick in strength, depending on how you formulated things. But the biggest thing that you're adding aggregates in there for is just to take up space and use less cement to fill whatever structure you're trying to construct. So next slide. Okay, so how do these mixes all come together, and how do we group things in terms of our terminology when we do waste management? So we'll walk through the life cycle of cement and how these different mixtures come together and what they make. But this flow diagram is similar for the other supplementary cementitious materials we'll touch on. So what we start out with to get to a cement product is we start with limestone and clay. You mix them together, put them in a kiln, animation. and you heat it up to about 1400 degrees Celsius. And what comes out of that kiln are these little nodules, and those nodules are called clinker. And what you've produced here, this is a material that contains that tricalcium silicate, that dicalcium silicate, those reactive compounds that will end up making those hydration products. So the nodules that come out is clinker. This is the main reactive component of cement. So they'll take these nodules, you'll grind them up into a fine powder, and then you'll mix it with some other chemicals. The other chemicals that you put in to make that cement mixture are things you can add in aluminum sources, you can add in lime, you can add in magnesium sources to tailor the resulting cement powder for a specific application. So there are a number of different types of cement. The most common ones are type 1, type 2 Portland cement, which is now essentially type 1L cement, which is Portland lime cement. So you would do those additives into it to get specific properties in your final material, but again, also to save cost. So depending on where your cement is coming from and how strict that country or that region's limits are on what constitutes a certain type of cement, a number of the additives that sometimes can go into it are strictly there to fill up space and get costs down. Because if you can use only 90% cement and 10% filler that goes into a bag, well, every 11th bag of cement you produce is free for you. So in good practice, the North American and European cements, very controlled, very strict, defined by the Portland Cement Association or ASTM, what goes into it. But you start to get bags of stuff at Home Depot that was produced in Indonesia or in India or in China, you see a lot more filler that goes into those mixtures. So start with lime and clay, heat it up, that produces clinker. Clinker is a reactive ingredient. That's the majority of the mixture in the bags of cement that you buy at Home Depot or you buy from Lafarge or whatnot. So then if we take that cement or that dry reagent, we just mix it with water, that gets us a paste. So once it hardens, you've produced a cement paste. If you take cement, water, again, add in sand to it, you get mortar. You get a relatively thick mixture, and this is what you use to hold bricks together. The reason for it is you're not having large aggregate in there to push your bricks apart. You can get anything nice and level. It's got good binding properties, but that sand is filling up space. So about 50% of the mix is sand. Therefore, using 50% less cement, your costs are going farther. That's why you use mortar to hold bricks together. And then if we make something that looks like a mortar, but we put some additives into it, some chemical additives to make it flow a bit more, this is traditionally what would be referred to as a grout. And these are the flowable slurries that you could use to go into the space in between the tiles in your floor. And one of the main challenges for me when I get to speak to university partners, when I say we use grout for nuclear waste immobilization, this is where people's brains go to right away. So I like showing these slides, I use these slides so many times. And yes, this is our traditional definition of grout, but we'll go get to in a second why we call everything grout. So the mixture of cement, water, sand with some additives gets you a flowable material, that's a grout. And then if you add in coarse aggregate, you start throwing in some rocks, that gets you concrete. My prior experience in cement concrete before coming to PNNL, my grandfather was a contractor, so I poured thousands of yards of concrete with him working it throughout the years. I never put two and two together why he would always, especially when I was really little, would send me out to go find the biggest rocks I could at the site when we were doing a foundation or something, and we would just get to throw them in. Oh, no, I'm just filling space. It was aggregate, but it's filling space. So that's how you get, that's the main technical definitions of the various types of products that you get when you mix cement with water and other fillers into it, either paste, mortars, grouts, or concrete. The animation. But within the DOE world or anything here in the US, if we apply this to nuclear waste immobilization or disposal, all of those can be referred to as grout. Next slide. The reason for that is a long-term kind of a multi-decade usage of it. So the way I've come to define grout, which I try to get as many people sold on, is the term grout is there to define use of any ambient temperature process, which may or may not contain cement, where water is used to react a set of dry reagents to generate a solid material that will be used in nuclear waste management. That's the best definition I've been able to come up with, and it seems to resonate when I talk to the academics, so I'm pretty happy with it. The origin of it is it goes back to one of the first waste cleanup missions within the US at the Oak Ridge, where the intermediate level liquid waste, the salt waste, the disposal process for them was they were going to be mixed with a set of dry reagents, produce a slurry, and then injected down into the shale formations at the site. As you do the injection down, the shale formation starts to fracture, the slurry runs out, and you spread it out, and you trap it down below the surface. That process looks very similar to borehole grouting or fracture grouting. So in the early documents, this process was referred to grouting of the waste. And since that point in time, throughout the US, when we use it for waste immobilization, we referred to cementitious materials or ambient temperature process as grout. And it's sustained all the way from the Oak Ridge timeframe. And if we take it from the view of it's not just one specific mixture of cement, it's not just one formulation, it's any use of those fundamental set of reactions where we take dry reagents, mix it with water, and then we apply that resulting material in waste management, that's grout. Where this gets a little tricky, especially when I talk to the Europeans do a lot of geopolymer development, which you can think of as cement-free grouts. Those are also considered grouts for us, even though there's no cement in it. It's a slightly different set of reactions. I've got a slide on it in a bit. But again, anything that's produced at ambient temperature, close to room temperature, maybe a couple degrees above, that's grout. Okay, back over. So in those 4 types of materials that we would call grout, where do we apply them in waste management? So you just hit all 4 animations. The first one, paste. What we would produce when we do liquid waste immobilization, such as producing saltstone at the Savannah River site, that resulting material is a paste. It's just a set of dry reagents mixed with a liquid and looks no different than if you just mix cement and water. So nothing else gets added into it. You're just using a set of dry reagents to design properties to properly react with that liquid and its chemistry. Next one. So then if we moved into solid waste encapsulation or stabilization of particulate materials, in this case, depending on what the material is, what the disposal site is, and what our desired properties are, we can use paste, we can use mortars, and we can use things that are more flowable like grouts. Paste and mortars are things that we would use for particulate stabilization or macro encapsulation. So if we have HEPA filters and we want to encapsulate them, you'd use something that looks like a paste or a mortar. If we've got a spent melter from a waste treatment plant and it's going to be encapsulated for disposal, you would use something that looks like a paste or a mortar. On the grout side of things, that's something we would use if you're trying to do maybe more facility closure. So if we're D&Ding a facility and you wanted to fill out into a void space, something that looks like a grout that will run and flow, likely used. And then concretes are things that look a lot like what we've used in void filling or in tank closure at other sites. So mainly the tank closure they've done at Savannah River site, those materials are very, very similar to concretes. Conventional concretes, although tailored to be far more flowable and have ideal set times. And if you are filling a 1 million gallon tank, you can continually operate and get a resulting product, but it looks a lot like concrete. Okay. So, I'm telling the story of we add other things in. And if you're doing this from an industrial standpoint, the main reason why they go to add other things into the cement is to save costs. They do get some control over properties, but their main driver is less cement equals less money. In our world, the use of supplementary cementitious materials really lets us get control over engineering targeted properties into our grouts that will be used to meet the specific waste immobilization challenges. All these different components that we can take from industrial byproducts that have similar hydration reactions, we can use them and their individual properties to tailor our materials to meet specific needs in our waste management challenges. So the technical term for these are supplementary cementitious materials, things that aren't cement that we add in to grouts or cementitious materials to make our final products. These supplementary cementitious materials can have different sources. They can come from natural sources, which we would call pozzolana, which means a naturally occurring material that has pozzolanic activity. Pozzolanic activity is the ability to react with water and a bit of calcium to produce those hydration reactions. And these are mainly aluminosilicate materials that come from volcanoes or from prior volcanic activity, which in its fundamental sense, you have a mineral that contains calcium and silicon and aluminum, got exposed to very high temperature, gets powdered down, becomes reactive with water. It's no different than what happened with that cement, where you took limestone and clay, cooked it at a very high temperature, produced a powder that can react. But the other source of them, other materials that have pozzolanic activity, we looked at things that come from industrial byproducts, and I'll touch on a few of these in a minute. And again, these play a crucial role in our ability to tailor specific properties. So I'll go through a couple of the key examples of them. So one of the first ones and one of the most widely used supplementary cementitious materials in industrial applications, and one we use in a lot of our waste applications, is fly ash. So this is a byproduct of coal combustion. It's a waste product that just sits in piles at the coal production facilities. It's a fine powder, depending on where you get it from, how fine it is. There's about 40 million tons produced annually. It's used quite heavily, especially in bridge construction or in precast applications of cement. And there's two main classes of it. Class C, which is a fly ash that has high calcium, a key component of doing those hydration reactions. And then Class F, which has low calcium, but usually a little bit cleaner. But again, it's a calcium aluminosilicate material that comes out of a high temperature process. The resulting powder has pozzolanic activity. Go to the next slide. So what do we use it for in terms of waste forms? One of the biggest uses for it is it improves workability. So it improves how, when we're mixing the dry reagents of the liquid waste and water, the fly ash really helps with the rheology of that resulting slurry and keeping it flowable and keeping it movable. The reason for that is pretty practical. The little fly ash beads that come out are look like little tiny ball bearings or little balls. So physically in the mixture, if things are moving around, if you have sharp edges, they can physically run into each other, and that makes mixtures thicker. But these little balls of fly ash are in there, they're just rolling around in the slurry. So it really helps us be able to mix some traditionally be a tougher mixture together. It decreases the amount of water we have to use. It produces less heat, so you have lower energy there. You can delay set times. And the introduction of fly ash is actually crucial to the production of the saltstone waste form at the Savannah River site, because they take their waste, mix it in a central facility, and then they have to pump it out to the large soap disposal units. The introduction of about 45% fly ash in their mixture actually helps with sustaining flow of the slurry through that line and into the large vault, specifically because of these properties. So we use it quite a lot because it does, again, give us good control of our rheological properties. Next slide. The next big one for us is blast furnace slag, which is a byproduct of iron production. So again, we take iron ore, you put it into a high temperature process. You're trying to separate the iron from everything in the ore that it's carrying it. And the resulting material that comes at the back end looks a lot like a glass. And you combine the limestone that's used as a flux in the processing. And what you get is slag, blast furnace slag. Again, material that contains calcium, aluminum, silicon, comes out of a high temperature process. You take that glass, you grind it down, it becomes reactive. It's usually a very fine particle size, it's about 10 microns. And when you grind it up, you get higher surface area, it becomes more reactive. The composition of it is dependent on what your iron source was, but a lot of iron sources come from the production of, or the original ore is pyrite, which contains sulfur, and the sulfur is a key component for us in waste mobilization. Let's go to the next slide. What the sulfur does is it provides electrons and a reducing environment, which helps suppress the release of contaminants and in our case radionuclides by reducing them to a lower oxidation state. So one of the fundamental mechanisms of why saltstone works for low-level waste mobilization of the Savannah River site is their work in the 1980s to develop the saltstone formulation. The inclusion of blast furnace slag greatly suppressed the release of chromium in their waste, which it showed marked improvement in both the TCL, we'll touch on this in a second, in TCLP tests and long-term leaching. Because the blast furnace slag comes in, it brings in reducing capacity primarily from its sulfur component. That sulfur component will go out to the contaminants that are redox sensitive, which chromium is. They can get involved in the redox reactions and reduce those contaminants from a mobile state to an immobile state. It has other benefits from a cementitious standpoint. It gives us some control over workability, how much heat is generated, porosity control. But the biggest piece in waste mobilization, if we're using slag, is it's in there to help with contaminant retention, both in short-term qualification testing and long-term performance. Because the slag glass itself, just like the cement, doesn't fully react. In our waste forms, we still see little slices of slag glass. So over long periods of time, that slag continually dissolves, continually releases those reducing species, and helps build in some long-term retention mechanisms to the grout waste forms. So, next slide. Another key addition is admixtures. So admixtures are chemical components that we can add in to get control, mainly during processing of the material. So these can be very complex engineered materials that Dow Chemical makes, or things that Dow Chemical will tell you are very complex materials, but they're just molasses dissolved in water. Not lying. What admixtures are designed there to do is if we can't get ideal processing by the introduction of fly ash or blast furnace slag, or maybe our waste chemistry isn't ideal, we can add in different chemicals to accelerate or slow down those hydration reactions. One of the main processes that admixes do is you can think of it as they can act as set retarders, so they can protect the cement particles and avoid water from getting to them. If water doesn't get to the cement particle, it can't dissolve, it can't be involved in those hydration reactions. So when you put a super plasticizer, a set retarder in, it's an organic compound, goes in, finds the cement particle, coats it, and it will slowly dissolve and water will slowly get to the particle and you will slow down those rate of reactions, therefore slow down your set times. Practical application of this is if you are doing a small concrete job in your yard and you make a mistake, which happens to many of us, and you end up with concrete where you don't want it to be. The way to solve that problem is you run inside, you get a bag of sugar, and you dump the sugar on top of that slurry concrete. The sugar is an organic compound. It'll go seep out the cement particles. It'll coat it. It'll slow down that rate of hydration reaction, and you can shovel the slurry, move it around, dispose of it. No one will ever know. Same concept, what they're doing with admixtures. So depending on what the target is, yeah, one of Dow's major admixtures is molasses dissolved in water for that specific application. Just coating things. And we use it as we get to some of our low water content mixtures where we're trying to get low porosity. We lean heavily on chemical admixtures to help us be able to produce our final waste form that has the target properties. Next slide. So just some quick examples of other supplementary cementitious materials that are emerging a lot more in both industry and in our spaces. Silica fume, which is referred to as flour in the cement industry, a byproduct of silicon wafer production, which we have as we, from a general sense, we move away from coal production globally, but we're going to produce a lot more chips. We get a lot more waste silica fume. This material is great. Again, very, very fine powder. It's used as a space filler. We have gaining inventory or growing inventories of it globally. So we're seeing a lot more use in the cement and concrete industry. And on the waste side of things, we like to play around with it when we are doing geopolymer development because it helps fill void space in the material. And if you have less porosity, you have less transport, less water in, less mobility of transports out. So silica fume is an emerging one. Next slide. Metakaolin is another one. It's just a calcined kaolin clay that's used heavily in geopolymers. It's an ammosilicate material. You add in some high pH solution, it reacts, makes a solid mass. And we can even have, this isn't one we do in waste yet here in North America, but some of my colleagues in Southeast Asia do. So you've kind of seen a theme here of any material that has pozzolanic activity. It's a natural material, expose it to high temperature, becomes a powder that's got reactivity. Well, what some very ingenuitive people have been able to do is take the husks from rice, and when they burn it for energy sources, the resulting powder has pozzolanic activity. So rice husk ash has been an emerging supplementary cementitious material, especially in Southeast Asia, and showing as a promising candidate to replace fly ash as we see global fly ash amounts start to decrease. And this could be a possible replacement. So the cement community looks broad and wide for other supplementary cementitious materials, and we put our finger on the pulse of that to make sure if they learn something, we always want to be trying it in our Grout applications, because if we're doing waste mobilization, we want to be using the best materials and the best design that we know to date. So we're always trying to learn. And there's a quick note, I mentioned geopolymers early. The difference between geopolymers and a traditional hydraulic cement is in that cement and growing the hydration products, you get dissolution and then precipitation of mineral phases that start to link up. At its core, what a geopolymer does is you use something like a metakaolin product. It still has calcium and silicon and aluminum in it. But in this case, instead of growing minerals, what you do is you start to get polymerization, where the various silicon atoms start to link up with one another and bond together, and you end up making a solid mass. Although in waste immobilization, and in my opinion, geopolymers in general, really is a gray area between what you call a hydraulic cement and what you call a geopolymer, because once you add in things like slag and fly ash to a geopolymer, you start to grow some traditional hydration products. It's not pure polymerization. So to me, geopolymers is just a broad term that people throw around if you don't have cement in your system. So, next slide. And this one's hard to see on the screen, but what this shows is things with the higher calcium content are your traditional cements, but as you lessen the calcium content and start to increase your alkali content, that's how you move into more traditional geopolymers. This is a slide from John Provis, one of my colleagues who's on a EMPA in Switzerland, but one of the kind of global leaders in cement research. And I always think it tells a good story, especially to cement students. High calcium, your cement, as your calcium amount drops out, which you do by removing the cement, you end up in geopolymer territory, but they're not all polymeric products in the material. So next slide. But in our case, if someone's talking a geopolymer, it's still a friend. Okay, so what are some of the key properties that we would want to control when we're doing various waste immobilization challenges? And they get binned into 4 different classes. Fresh properties, cured properties, ones related to performance, and then aging of the material. What dictates the properties when we're doing waste immobilization? It starts with the disposal site itself, or where this material will be employed. Once you know the requirements of your disposal site, you then start to back engineer into what properties does my material need to have to ensure that we meet, whether it's waste acceptance or long-term performance requirements, to serve in that application. We use that to help define, okay, what are our candidate formulations that we could use to get us these target properties? And then we look at the waste stream itself. Okay, what chemistry is it bringing? What physical properties is it bringing in? Will these formulations work for it? And can we produce a final waste form that has those properties? So the way this flows through, the fresh properties are things that help us process and produce the material. The cured properties are our target final end game that we want to hit. The performance is what we like to see those resulting properties lead us into. And then those performance properties get influenced, depending on the application, by how that material will age with time. So the key fresh properties that we concern ourselves with are flowability, which is just when we do that initial mixture and it's in its slurry state, how easy does it run? How viscous is it? In cement concrete, you would use what's known as a slump test, where you take a big cone, fill it with your material, pull it up, and it makes a hat. And however far that material slumps down, gives you a sense of flow. We use tests very similar to that to give us a sense of how flowable material is, all the way up to advanced rheological measurements, where we're trying to get a sense of how flowable these materials are. Usually what our goal is more flowable if we want to do encapsulation, less flowable if we're mixing and keeping in a container. Heat generation is always a control of us. When these dissolution hydration reactions happen, we get release of heat. If you produce too much heat, the reactions start to accelerate and you can get a flash set. Usually when we're adding in things like fly ash and slag, that really slows down those processes where that's not a concern for us. But in geopolymers, especially when you add in some of the waste components, you can get a lot more heat generation. So we always monitor for how much heat is generated, how long it takes for that heat to generate. It gives a sense of the reactions that are occurring. And when we go from laboratory to scale up, is one of the things we like to monitor. In terms of once that material starts to harden and it gets to that set stage, because it's trying to react with as much water as it can, you can still have some free water. And if you're not smart with the way you designed your material, you can end up what's known as free liquids or bleed water. So that's where you have a cured material and you end up with the liquid sitting on top of it. Eventually what happens with most cements, that liquid will become reabsorbed and consumed just a couple days later. But if we're doing waste management, one of the main guidelines that's laid out in the NRC technical guidelines for waste forms is you want to have less than 1% of free liquids on your material. Because if you're immobilizing a liquid waste, that bleed water that's sitting on top is your liquid waste, essentially. So you don't want it, you want to be designing mixes that don't produce a lot of free liquids. Fairly straightforward to do. And nearly all of the ones that we've evaluated in the last decade and a half for waste immobilization here at the site, you see reabsorption of any free liquids within a day. So from a processing standpoint, you don't want free liquids sloshing around when you're moving it. So most waste forms meet that requirement. And then the final thing we want to do from a processing standpoint, we want to know how long it takes to set. You don't want it setting in the mixer, but the quicker it sets, the quicker you can move it down the assembly line and move it out towards disposal. So it's always trying to find a balance between something that we can continually process. If you have a continuous process, similar to what WTP has or what Saltstone uses, you don't want quick set times, but if you're doing more batch mixing, quicker set time is good because you can mix it up, ensure it's set, move it on. The cured properties that we concern ourselves with, density of the material, that's weight and shipping if you're transporting it, but also gives us a sense of how much porosity there is. There's a direct correlation between more porosity you have, more easy it is for water to flow through. Therefore, it's easier for contaminants to flow out of it. So we usually target materials with low porosity, high density, compressive strength. Not as big a requirement in waste disposal because it's not a structural component of the facility, but we still want materials that handle, that you can move without them trying to fail. But nearly all of our materials are well above 1,000 PSI. Even if we try to make a bad material, it's hard to get it down. The degree of saturation. So once you've made the material, how much free water, how much of those pore spaces filled up. When we do liquid waste immobilization, that saturation point is near 100%, and it will stay near 100% for the majority of the life of that material, even if it's sitting out in the air and Hanford subsurface. These materials like to retain that water, and if new water comes by, they want to suck it up to continue those hydration reactions. And then the resulting porous network, how tortuous it is, so how tough that pathway is. If you've got a lot of big pores that are connected, easier pathway, but if you have smaller pores, less likely they're connected, harder pathway for water to move in, and contaminants to move out. And then the overall mineral makeup, because we use that in long-term modeling to how this material will evolve with time, but it also helps us confirm that we made the target product that we were after. In terms of performance, this is where disposal site most heavily dictates what we shoot for in terms of properties. Leachability is a prime for doing waste immobilization. You're trying to isolate a contaminant or radionuclide, whether it's in a nuclear application or a wastewater application. The rate at which components leach from that waste form is key. But if the disposal site does not present a pathway for those contaminants to re-enter the biosphere, you're usually looking at some more strict threshold type leachability items. But if you're going to a disposal site where you have a pathway to the biosphere or a pathway to groundwater, like the Hanford IDF, you're concerned about long-term leachability. How long, or what does that 1,000-year term look like? And the way we study that is we try to make links between short-term tests where we can screen materials in the laboratory to longer-term laboratory tests to very long-term field tests to looking at things like natural analogs. So what we try to do is study and screen our grout materials in the laboratory in reasonable time frames in our leachability tests. There's a number of them. We then take promising materials, do longer tests on them so we can understand their longer-term evolution, do those longer-term tests in representative conditions, and take very promising things and put them in more of a realistic field environment. Then when we take our long-term dissolution models, whether it's for a glass waste form or a grout waste form, and we apply it, we can replicate the behavior in those short-term tests, those long-term tests, those realistic tests, and those field tests, and we can take our models and replicate the behavior that a natural or ancient analog has. That gives us confidence in the ability of our model to predict long-term performance with associated uncertainty with it. No model, when we're extrapolating it out 1,000 years, is going to be 1,000 years, 10,000 years, a million years, is going to be 100% certain. But by applying our models to tests in the laboratory at various time lengths, it gives us confidence of what our error bars should be as we project out. And that's where you get confidence in decisions and materials we're going to apply. Other performance properties, or I have to say the main leachability tests that we do, TCLP is used as a worst case scenario screening test. TCLP is designed to screen materials that go into landfills. It's kind of a very bulk extreme environment test. You take your material, put it in a strong acid, crush it up, put it in a strong acid, see how much stuff is released, and do you stay above or below a threshold. The information that gives us on the grout side of things is it shows us if some of the retention mechanisms that we've engineered into our material, if we still get lower release in a TCLP test, that gives us high confidence that in our realistic disposal environment, which is usually neutral to alkaline, things are going to perform well because we went very extreme where we'll never see high acid and things still perform well. An example of that, blast furnace slag. You take a mix, you put chromium into it, mix it with just cement, you do a TCLP test, it fails. If you do a mixture of cement and blast furnace slag, you put in the TCLP for chrome, you pass. Because the blast furnace slag reduces the chrome, when you get into that acidic condition, the chrome's not mobile, it's stuck in your solid, it doesn't release as fast. The more practical and representative tests are the semi-dynamic leach tests, where we take a sample that's now not crushed, monolithic, put it into a solution of water, let it sit for a period of days, measure how much stuff is coming out. Being immersed in a large bath is still a very conservative scenario for a grout waste form, but it gives us very valuable information to compare rates of release of different contaminants and see how our mechanisms that we've entered into it, if they last for several days, several weeks, several months, several years, and it gives us data that we can model it against And we can do those exposures in different pHs or different groundwater environments to see how things change. And those semi-dynamic leach tests, there's a number of different ones. EPA has their method 1315, American Nuclear Society has method 16.1, ASTM has method C1308 and 1220. Everyone's got similar variants to the same technique. Take a monolith, put it in water, measure how much stuff comes out. And then we take it and we go to field exposures where we do tests in columns in the laboratory or a lysimeter test like we have ongoing at the Hanford site right now. Other performance parameters are the main one is how fast can water move through the material. Therefore, if you make a very impermeable material, low water transport, low rate of water going in, low rate of other environmental species going in, low rate of release. And then in terms of aging, again, depending on the application, if your disposal site presents a pathway to groundwater or back into the biosphere, we want to know the long-term performance of the material and some processes that we want to be evaluating in the laboratory and developing modelings for how our contaminants behave over long time frames, the rate of carbonation of our materials, the rate of oxidation, because those change the properties within the grout, again, depending on how you engineered it, for better or for worse. Cracking, and then the overall mineral evolution. Because like I said at the start, grouts are not static materials. They continually react with time. Those reactions can be pretty good properties into the material, or if you're not smart about how you designed it, negative properties. So go to the next slide. So how do the various contaminants behave within cementitious materials? I touched on this a couple times throughout the presentation. So cementitious materials are widely used for low-level or hazardous waste mobilization throughout the globe, not just in the nuclear sector, but for handling wastewaters as well. Cementation is the BDAT for most of the D-code metals and some F-code aqueous waste that contain metal. Mainly, it's the metals that will precipitate once you get to a high pH. So if you remember from the start, that fundamental chemistry, one of the products that we make is calcium hydroxide. That makes a high pH environment that stabilizes the calcium silicate hydrate. Well, high pHs also lead to precipitation of many of the hazardous metals. And if they precipitate down from a soluble state to an insoluble state, they're not mobile, they're contained within the waste form. We can also get that suppression by building in reduction mechanisms into the waste form by adding slag or by adding iron or adding sulfur in. And this will also suppress the release of metal species and some redox sensitive radionuclides like technetium. If we're doing liquid waste immobilization, what happens when we mix our dry reagents and that liquid together? So that liquid contains this range of chemical components, contaminants, and in some cases radionuclides in there. As the dry reagents start reacting with the water starts to get consumed. Where the pores come from in cement is spaces where there used to be water. It is a way to think about it. There's a decent correlation between your resulting porosity and how much water you started with. So as you start to consume water and make those mineral networks, the pores that are left behind, those salts that are resulting from that dissolving liquid waste, they start to be present, concentrated in that pore space. And that's where the chemistry happens. So if we design a reducing environment into our waste form, within that small little pore structure, that's where the dissolved sulfur from the slag will interact with the chromium or technetium and do the reduction and precipitate it out. In some cases, in some grouts, we can get those contaminants to go into the mineral structure of the grout as those hydration products are growing outwards. In other cases, they'll precipitate as just discrete products that we can go in and see on the microscope. And other elements, maybe ones that we're not as concerned with or ones that are more challenging, will just exist as salts in that pore volume. Things like nitrate and nitrite, harder to get into the matrix of a grout, so they'll mainly sit in that pore space, and then their release becomes dictated by the rate of water movement in and out. That's a general sense. I could spend a whole lecture going through one by one what happens with each of those in different grouts, but that's a general sense is when we do that, the takeaway from there is when we do the hydration, you still get the same fundamental reactions, but as you start to create those pore volumes, that's where the chemistry happens, and that's where the contaminants either get incorporated into the grout, precipitated out, or persist in that pore space. Went over this already. I thought I had this as an animation, but some of the main leach tests, TCLP, the semi-dynamic leach test, and then to get to more real world conditions, especially in our application, unsaturated testing, which takes a very long time because you don't have a lot of water nearby. But again, we want to ensure that the models that we develop to predict long-term performance can replicate behavior, whether it's in short-term aggressive tests, longer-term representative tests, yield tests, or analogs. We always try to build our story out so we grow confidence in the materials that we are providing data for folks to make decisions on. So, next slide. this, again, something I spoke ahead of before. The main property driver for us, this is one of the takeaways I try to instill in my staff, is when they get tasked with designing a formulation or making a matrix of what we're going to be testing for to meet an emerging need, whether it's H2C or DOE comes to us and said, hey, we have this potential waste stream. What are our candidates? What can we do? What I try to get my people to think about is start from your disposal site and work your way back. If you're going to a disposal site that does not have a pathway to potable water or does not have a pathway to back to the biosphere, so such as the Energy Solutions Facility in Clark, Utah, Waste Control Specialists in Andrews, Texas, those disposal sites, just from a general waste disposal standpoint, are geographically ideal. They're isolated. There's no potable water at those sites. So their waste acceptance criteria becomes set on land disposal limits and inventory limits for the radionuclides. Because if you put the waste forms and the contaminants into there, they're not going to enter into the biosphere. So for example, at the Clive site, you're sitting right near the salt flats, you decide to show up, drill down and start drinking the well water, the salinity is going to do a lot more damage to you in a shorter time period than any of the uptake of contaminants that may exist at the site. And that's in general how their performance assessment of that site is constructed. Is what is our impact? Well, pathways to potable water and groundwater are very limited to non-existent. Therefore, they set limits based on waste classification and inventory limits of how much of a radionuclide they can take. And they have specific property requirements of their waste form that they can have ideal disposal scenarios within their site. But again, if we're going to a disposal site or the material is going to exist where you do have a pathway to groundwater or potable water, then you're going to want to be engineering in better retention, strong inventory control, and ensure we understand long-term aging mechanisms, because we're going to want to be assessing impact over the required timeframes. So when my team gets tasked with this, we always start with disposal site. That's what defines our target properties. We make a list of candidates. Then we ensure, can we produce waste forms that look like that? When we go in the lab, verify we can produce them, ensure we have the properties we're targeted, and how those materials behave long-term. So it's kind of this walking back approach, which for me, having come into the waste mobilization challenge at Hanford about 10 years ago, really where there's been a paradigm shift for us in our considering of using alternative disposal sites to help assist the mission as a whole. So by being able to consider alternate disposal locations, it really opens the door for our waste treatment strategies and the types of materials that we can use to solidify the waste in a more economically feasible fashion without sacrificing any environmental risk. I think that's on my calling card of what I do as a researcher, is I try to find solutions for nuclear waste management challenges that are economically and technically feasible. We're using the best information we have to date, but we can implement these things without sacrificing any environmental risk. And the way that we do that, if you take a look at your disposal site, walk back into your materials, that really allows us to achieve that goal. So the final slide is just one quick takeaway. The three main applications that we deal with potentially here in the Hanford mission are liquid waste immobilization, where we're making things that look like paste, solid waste encapsulation, whether it's micro and macro encapsulation, where we're using things that look like paste, mortars, or traditional grouts, and then doing void filling, where we use things that look like concrete. So that's what I wanted to talk through. I hope that answered a lot of the information you guys were looking for. Again, if I missed anything, feel free. I can sit here all day. I can come back, happy to. So yeah, I'm sorry if I went long. I just left. I like giving this presentation. So thanks.
No, that's very good. Thank you. Yeah, there's tons and tons of questions that people would have a little bit, but I think that we should get a view from, maybe from ecology. If there's, this is kind of a one-on-one thing, so I don't know what.
So the way this one's set up is two back-to-back presentations. We want to hear from Ricky Bang on the testbed initiative, and then we'll jump to regulatory support cycles.
Okay.
You want to have questions for Matt first before we get into testbed?
I'm sure you really appreciate the master class. Let those build up for a second.
That was great.
Was this gone through when they did the grouting inside U plant?
Yeah, similar concept.
Okay.
Yeah.
How about the tunnels?
Yeah.
Yeah,
And
I
so
showed a picture of the tunnels.
Yeah, and the tunnels, so that in those approaches, you're going for more of a traditional infrastructure type application. We're just trying to fill a space. So the formulations that they use for each of those made perfect sense for what we were trying to do, which was fill a void space. And
One was looked at separately.
yes,
Just.
yeah, they were separate, and
Okay, that's good.
the Purex tunnel one, before or ARP, American Rock Project. Yeah, they just drew on prior information that existed of, okay, if we're doing closure, here's the formulation we would use. It looked a lot like a concrete, but was specific, especially in that application, we were trying to run out into a large structure, fill around a lot of voids. It was more of a flowable type material, but what they utilized fed by decades of knowledge here within DOE and just in general in applications as well. Yeah.
Interesting.
Just one question, please. Would your department be giving specifications for any of the waste that we would send offsite?
We wouldn't, let's say, so as P&L, we wouldn't define the specifications. Our role is providing data that shows that we meet specifications set by the disposal site. So if in our role of, I guess, say, yeah, so in our role, the way we've kind of been interacting and supporting DOE and H2C through the TBI process, and you know, the research going into understanding growth for IVF disposal is we look at what the requirements are going to be at those sites, which are defined usually through a performance assessment by that state. And then we will screen formulations to show for that specific waste streams, what formulations could meet the required properties. And kind of usually what we strive to do is give a couple options back to the contractor or to the general public of here's what could be used. So if you select any number of these, you're likely to meet the properties. And if you make a decision on one, then a big piece of what we do is qualification testing, which is very rigorous. Here, we ensure that with the variations in the waste, and we've been doing a lot of this for the liquid secondary effluents that'll come out of the ETF that'll be disposed of at IVF. Ensuring that if you've got variations in waste chemistry, here's how the properties might change and be able to show and lock in that yes, with fluctuation in chemistry, if you use this formulation, you'll consistently meet properties. So once you get into production, you can do some spot checking along the way and build confidence that yes, we're making this consistent product. And that's one of the other beauty benefits of using cementitious materials or grout is they're fairly malleable in terms of how they respond to changes in chemistry and still produce the same properties. So
will Utah and Texas, their grout?
the vendors themselves have grout formulation or treatment recipes that they would apply to that waste stream that would meet the requirements for their site. And we at P&L have been working with them over the last year and a half, 2 years of doing some testing of, yeah, here's what happens when you use hand tools for it. And yeah, they have very smart people on their ends who have a history of waste treatment, and they have a very good sense of what they will produce to meet the requirements at their site. And we've been helping produce data to show that, yes, you're going to consistently get it. So again, and they define those based on the requirements of the disposal facility they operate.
That's really interesting. And that also really makes it important for the waste to be grouted in those locations.
Or ensuring that whoever's receiving the waste is working with the producer. I think that's a bigger takeaway is ensuring that those lines of communication always remain open. I know there's different commercial entities that could be at play, ensuring that they talk to one another, which they would. But the companies that own the disposal sites have a long history of doing waste treatment and disposal. We have a breadth of information of other candidate routes that could be used that's out in the public. They can pull them in as they see fit as we go forward in the future. The way I communicate to the disposal vendors is I'm always here to help. If you need things tested in the laboratory, we're Hanford specific. We have the expertise. We're here to help you guys. But they have waste treatment experts on their end. But eventually, as we get into the mission, if we do realize direct stabilization of pre-treated waste and we're taking it off site, if it's produced here or at local at those sites, you just want to ensure the disposal vendor has communication to whoever's producing it. So we're making products that meet the requirements at those disposal sites because they vary, because their disposal constructs are different. So.
Thank you.
Super quick, guys. Yeah, we need to hop into Ricky's presentation. No, you're fine. But that way we can get that presentation going and then we have time for questions. But
Andrew, sign up.
We don't have to, and we can just let Ricky go back to work.
I think while we have Matt here, that's always a good use, but, yeah, I can cover this pretty quickly and then, we can continue on. Give Matt a chance to breathe and,
Perfect.
yeah, that's excellent. But yeah, good afternoon, everyone. Ricky Bang. I'll provide an update on the 2,000 gallon test bed initiative demonstration today. Next slide. And this informational update, it's kind of a follow-on, I think, from the full board update kind of gave on the tank waste mission, but also the holistic agreement. So really, as part of the holistic agreement, we're continuing to maintain our commitment to deliver on the direct feed low activity waste approach. And then in parallel with the direct feed low activity waste approach in the 200 East area, through the holistic agreement, we agreed with the state of Washington and EPA to also treat tank waste to immobilize it in grout and dispose of it offsite outside the state of Washington. So we had also performed a 2,000 gallon test bed initiative demonstration to test both the regulatory processes and the physical processes for the grouting and out of state off-site disposal of 2,000 gallons of tank waste. Next slide. So we had performed a 2,000 gallon test bed initiative demonstration. We had fabricated the equipment, installed the equipment in SY Farm in the 200 West area. The equipment was installed in October, operated the equipment and treated 1,961 gallons out of tank SY101. Now from the material that was treated there, they were stored into 6 totes, which were then shipped at the end of April of this year to Clive, Utah and WCS in Andrews, Texas. And again, that was at the end of April. And I think there were some animations on this slide to kind of point out some of the equipment that we installed in SY101, including the pump and ion exchange column that went inside the tank, secondary equipment towards the delayed tote. Let's just click it through item number 6, I think. Delayed tote confirmed that the ion exchange column did operate as intended. And then the storage totes in yellow stored the 2,000 gallons of pre-treated liquid waste in those totes. And then those yellow totes we use for transport of the material to Utah and Texas. Next slide. As part of the test bed initiative research, development, and demonstration permit with the state of Washington, there were 6 objectives that we included in the permit. They're listed there, but through the operations and of the test bed initiative equipment, we demonstrated that we can filter solids and remove cesium with the system that we installed into SY101. Through the sampling of the pre-treated material, we verified that the treated waste met the waste acceptance criteria for the disposal sites in Utah and Texas. Objectives 3 through 6 will be demonstrated as the vendors in Utah and Texas go through their treatment processes, perform the grouting, and then dispose of the waste. And we should be getting final reports from both those sites this year. Kind of the next couple slides I'll go through pretty quickly. There's probably a couple of good photos towards the end of this. But again, the first objective was the removal of cesium, which we demonstrated 99.99% of the cesium from what was in SY101. We showed based on sample results were removed by the ion exchange columns based on the sample in the storage totes. And again, no settled solids were found inside the transport totes following the test bed initiative treatment. Radiological surface dose was less than 0.5 millirem. And we couldn't measure less than that because the background radiation was about 0.5 millirem. Next slide, kind of put that into context. A radiological dose, that's about what you would get from a dental x-ray from your annual visit to the dentist's office. Next slide. Objective 2 had to do with meeting the waste acceptance criteria for the disposal locations in Utah and Texas. And so based on the criteria that those sites had for their radiological waste classes, free phase with the organic contents and the LDR organic concentration, our sample results demonstrated that we met all of those criteria for the shipment and transport to those disposal locations. Next slide is based on those samples results that we received back in April. We were then able to transport the containers to Utah and Texas. And so those containers, those yellow containers that you see in the upper right, they were loaded onto the back of the trucks that you see there on the upper, well, in the other 3 photos. 3 containers to a truck, and then inside of a kind of a trailer that's a bit enclosed. And then everything was strapped down and shipped to Utah and Texas. They were received at both facilities. And these were photos taken at the very end of April as the trucks left the Hanford site. All 6 totes arrived at the destinations in early May. Today being, I think, the first week of June, kind of the latest and greatest updates that I shall share is that the shipment that made it to NHG Solutions in Clive, Utah, I can confirm that last Thursday, half of their TBI waste was grouted and disposed at Energy Solutions. So that's been at least physically confirmed, and then we'll get a final report in the next coming weeks. For the fraction that was sent to WCS in Texas, they're forecasting to have theirs grouted and disposed at the end of this month. And so once that occurs, we'll provide the information as we get it. So that's the latest and greatest with the testbed initiative shipments and its status. So at least with the waste that went to Clive, Utah, preliminarily, it's been a success, and we're looking forward to that continued success at WCS. So far so good. But I think that's been a good step in the right direction to demonstrate that we can have a step towards meeting our commitments with the holistic agreement, and we'll continue to work through the processes, the regulatory processes to kind of achieve the outcomes and the commitments that we have in the holistic. Any questions on kind of where we're at with the testbed initiative?
I can provide a quick kind of ecology kind of comments that we had. So I know Suzanne wanted to be here today, but got kind of tied up. So I was going to provide a couple kind of high level remarks and also keep it short and sweet so you guys can ask your questions and then see if Dan had anything I might have missed. But we just wanted to share, we really appreciate the presentation and the conversation today. And as Matt covered, there's a lot of other uses for, grout and Hanford site beyond tank waste. And he gave the same example I was going to give about like grouting for Curex tunnels, for example, to stabilize those. So there's a lot of kind of non-tank waste kind of uses that are being employed at the Hanford site. But specific to tank waste, we support grouting low activity waste for offsite disposal. And I think we've demonstrated this through our report of the 2,000 gallon testbed initiative demonstration that Ricky was just providing an update on, as well as the recently finalized holistic agreement, which I won't get too much into because I know we just talked about it a couple weeks ago and Ricky's been talking a little bit about it. But so, we think grout has a place in the tank waste treatment toolbox when paired with appropriate offsite disposal sites with more robust geology. So we think Hanford's not an appropriate place for disposal of grouted low activity waste, given Hanford's geology, depth to groundwater, and proximity to the river. But kind of veering to TBI and where we're at with TBI, we were really encouraged to hear that Energy safely completed those TBI shipments to Utah and Texas. And And as a kind of a quick refresher, we provided some support on the TBI project by issuing the research development demonstration permit to Energy for the on-site waste management activities that happened at the Hanford site prior to shipment. And then as Ricky shared, under the holistic agreement, separate from CBI, Energy is going to be retrieving waste from 22 tanks in the Hanford's 200 West area. The low activity portion of that waste will be grouted for offsite disposal. So we just look forward to continuing to advance that project with Energy and EPA. Alongside, as Ricky said, the continued vitrification kind of mission and path for low activity waste and high level waste at the waste treatment plant. Dan, did I miss anything?
A little history, if you don't mind. Matt and Ricky, both, thank you so much for your presentations. One of the concerns I continue to have is that we still seem to be in either a bench scale or an R&D perspective on the grout and how it's to be used. And let me take you back a few years. In 2003, Tom Bronson Company did a preliminary assessment, and they came up with upper and lower bounds, yet no diffusion criteria or release rates. You come forward by 2015, there was a P&L report on getters to improve cast stone performance. And again, no definitive results on that relative to Hanford tank waste. Moving forward, Matt, you in 2019 had a presentation on grout properties and research advancement. And on slide 10 of that, you indicated that there's still significant protocols and steps, to my words, proving efficacy. Keep moving forward to 2023, and this is on secondary waste. There's this thing called ultra high performance cement-based composites, and it was Bernard's, Nichols, Kaplan, and others. They speak to the idea of having potential for use, but again, caveats. And then we come to today. What I am continuing to hear is we're in the process. We are past being in the process for R&D and get ready. We're going to be moving into production mode here in the next few years. And I'm continuing to be concerned for the West Side waste that we are not ready and we do not have, if you will, verified recipes for the different wasting we anticipate getting out of the SSX and U farms. And I'm wondering how the research is going to be significantly accelerated in order to get us to the point where we have actually production capacity to move this waste and grout it appropriately. And that's on the assumption, of course, we do it on site here. If we don't do it on site here, then the verification and validation of the amount of waste going forward to be grouted at other sites is still a concern. Over all of these years, starting in 2003 going forward, I have yet to see a solid nod how we're going to manage this on a production basis. And that continues to concern me. Over.
Thank you. I do want to confirm or check to see if we have anyone available from EPA to provide a perspective.
Yes, this is Michelle Mullen on the phone. I'm home with a sick child today, so I don't have my laptop, so I couldn't join on Teams. But I heard the presentations, and I was really encouraged to hear, Ricky, that the waste has been disposed at Energy Solutions. So that's very exciting. And I want to second essentially everything that Ecology said. EPA is also ready and willing to support issuing land disposal treatability variances for grouting and disposing of tank waste off-site. I think the TBI was, it was intended as a test, and one of the major things it tested was the regulatory pathway to be able to grout and dispose of tank waste out of the state of Washington, and it was a success. So future batches of waste that will be sent out for grouting and off-site disposal will need EPA variance approvals, and we're ready and willing to do our part to make that happen.
Very much. That a long awaited session for questions. So we have two people who've been patiently waiting. We have Matt and Mia online. I'll start with you, Matt, and go Mia and Chris.
Well, let me start with Ricky and then we'll go to Mia because I'm sure that I'll have plenty of questions for Matthew as well, Professor Asmussen. Ricky, do you know when we will have that data that for you meeting the objective 2? So your lab numbers, will we have that publicly available at all?
Yeah, I think as part of the RD&D permit, there is a requirement in there for us to produce a final report for the testbed initiative.
Yep. So that's going to be in the future after you get more data from WCS and Energy Solutions?
Yes, and I think we kind of had that action and commitment from the full board meeting as well. And I think Ecology also committed to trying to make that final report public from the full board meeting.
Okay. And yeah, and one general comment, you say that your dose right there at surface level is 0.5 mmR an hour?
Yeah.
And that was not distinguishable from background?
Correct.
That's a pretty beefy background.
Because the testbed initiative equipment was inside the fence line of SY Farm next to the double shell tanks there.
Okay. So you still get that much of a flux where you were
inside
with it. Okay. All right, thank you.
You're up next, Mia.
Okay, I have a lot of questions. So, Josh, maybe you can put me at the end of the queue after I ask a few. My first question is for Ricky. I'm just curious if Clive shared with you how much grout they needed per unit of tank waste to solidify the waste, that half the amount that was sent. Did they share anything with you?
I don't have the final report yet, and I know you asked during the full board meeting, and I still don't have the answer yet. I think based on kind of what Matt kind of talked about as well is the results from Energy Solutions and WCS. We kind of have to take that within context with whatever the result will be, because they may either mix the TBI waste with other waste, or they have a container that they then also still fill the void space with grout as well to kind of with whatever 900 to 1,000 gallons that we sent them, they'll probably just fill the rest of their container with the cement material, grout material, cement material to fill up the rest of the void space. But I'll say that once we get the final report as part of the RD&D permit, I think that should contain the information, or we'll have it at a follow-up briefing. But just whatever the result may be, that I think the context will also be important for that.
Okay, that's helpful. Matt, I have a number of questions, I think, specifically for you. The first is, speaking about tank waste and grouting tank waste, Hanford's tank waste specifically, if it doesn't solidify, is the trick to keep adding more grout until it solidifies? I mean, I know you talked about a lot of different additives and things today, which I don't fully understand, to be honest, but is the idea that if the waste doesn't solidify with the recipe that you keep adding more grout?
Yeah, and it's that scenario is highly unlikely with the nature of the chemistry of the Hanford waste. The components that if you get into a case where conventional routes wouldn't set or solidify, it's usually where you have excessive amounts of sulfate present, but there's ways to engineer to that. And the concentrations of sulfate that are present in the Hanford waste do not approach those limits where they would interfere with conventional cementitious approaches. And if you did get into that scenario, like any concrete use would be that if you were doing a mix and it wasn't setting, you would probably just add in some more reagents, mix it up, add in some more water, try to drive it to completion, or break it up and add it back into the process. But from a Hanford waste standpoint, for the work that's been done looking at waste compositions down from 1.5 molar sodium all the way up to 10 molar sodium between us and Savannah River over the last 20, 30 years. For that LAW, PTW composition, it's very difficult to get into a scenario where you would not set.
Okay, thank you.
So that's pH 1.5?
No, it's the molarity, so the molarity of the sodium. So
1 molar sodium is pH 14.
okay, so if it's sodium hydroxide, this would be all of those would be pH 13 where the waste usually sits, but it's nominally within the tanks, your 2 to 5 molar sodium concentration. So between us and Savannah River over the last 25 years, we've done tests pretty much from 1 molar sodium up to 10 molar sodium. So waste is in the middle, from a retrieval standpoint, if you had to add a ton of water at the end, maybe you get down to that 1 molar. If you put it through an evaporator, you're targeting 5 to 7 molar sodium. And then in the extreme case, if you can get it full up to 10. So we've studied it across that range. And what that gives us is scenarios where you've got a lot of water present at the lower molarity, and then where you got a lot of salts present at the higher molarity. And those do create different environments, but with the formulations we evaluate, that's where we get our information for how to design these materials. So having studied across those ranges and all the associated components that come with it, my confidence is always, can you make a solid material? Yes. It then becomes, are you making that solid material that has the required properties for whatever disposal site it's going to? And that's where our work comes in.
So how do we assure that the contractor is using your specification for that waste?
So the majority, I'll walk around this. The scenario we have right now, without going into details of the work that we do. So I have NDAs, the 3 directional NDAs with ourselves, H2C, and the disposal vendors individually. So we have open lines of communication and work of them sharing the formulation that they plan to use for the waste. The contractor is aware of it, they're funding the work. We're doing the work in the laboratory, providing that data to the contractor and back to the disposal vendor. So everyone's getting all the information of here's what we're seeing. We did some developmental work, some screening work of here's a simulated SY 101 waste composition. Here's how your treatment method worked for it. They did what they were intended to do. And then it's into questions of, like Dan kind of highlighted, is if you see changes in waste composition specific to West area, if we see any changes in the formulations, I don't anticipate changes, but that's work that we're doing for the contractor. So once you get to an operation standpoint, my hope is that the labs are always engaged with those contractors. That's part of my role at P&L, is engaged with the contractors, is that we would always be doing what we do as the labs, which is giving our best information out into the public domain and communicating that to all interested parties. So
somebody else's question before me.
That'd be Chris.
Yeah, I'd like to add one
Sorry, this is
thing to.
Michelle. Could I just answer also for EPA on that question of how do we ensure the disposal site, the treatment site, is using the correct formulation? The purpose of a treatability variance from RCRA is to ensure that the waste is still is in a form that is safe for disposal. So the disposal site and the generator, being DOE, will have liability if they're not able to meet the requirements of the treatability variance, which for TBI included performance testing after the grouting was completed. So there is that kind of a check on the back end that the grouting is done in an acceptable manner to meet the RCRA federal requirements. And if it doesn't meet those requirements, there are significant liabilities for all the parties involved, really.
Can I interject one thing though? That, you're setting requirements for it, and I imagine the requirements are going to include the physical properties. Yet less than a month ago. They got the liquid, they grouted it, and it's not cured yet. Your 28-day cure time is not, you're not that cured yet for you to be able to perform your testing. So I'm a little, how are we gonna guarantee?
But I'll give one piece of information on a way to conceptualize that. So the conventional standard is at 28 days, you would do your compressive strength test. That's the ASTM standard. So at 70 or 28 days, you do your compressive strength testing. But the disposal sites themselves and the treatment vendors, they have their requirements for what their formulations look like or what their formulations are for when they perform tests and when the material is set. And for them, strength requirements may not be. So the IDF, there's a strength requirement. At those locations, there may not be a strength requirement. In terms of studying the properties of it, those materials have obtained their properties within a couple of days. Usually, we in the laboratory will carry things. Usually, we look at 7 days and then 28 days, and 7 days you essentially got your properties.
Right. Thank you.
Thank you, Chris.
Yeah, I came from the Fernald site and we grouted all of our tank waste and shipped 3,700 canisters, 6 feet high and 5 feet wide to Andrews, Texas. I was the lead process engineer for the grouting in our plant and developed the recipes. And one of the things I wanted to bring up is if we have to grout here at Hanford, in addition to everything you mentioned, one of the key things in developing a grout is that it has to be compatible with the construction of the plant, the design of the plant. Before I got involved in Fernald, they took our tank waste, K65 waste. Contractors spent 2 years developing treatability studies, lab scale, large scale, that met all of your requirements here. And when we built the plant, by our contract with DOE, we had to do all this grouting within 9 months. The recipe didn't work because of the design of the plant. And the design of the plant, from when we got the waste, when we hydraulically mined the waste out of the tanks, through the plant, into the mixers, into the cask, the design of the plant altered the waste form. In that it significantly diminished the particle size of the waste so that the water absorbed around the waste. There was almost no free water in the waste anymore in the slurry.
Yeah.
When we took samples of our 40% solids, which were supposed to be liquid, they were solid. Thixotropic, so if you bump them, they liquefy. So we had to design recipes on the fly. And our production was very low for the first 2 or 3 months until we figured out what to do. But the key point is, if we build a plant here and design it, in addition to everything you said, the design of that plant and how you formulate the grout is just as critical as anything else. It's as critical as the chemistry of the grout, the waste form of the grout, and that's something that really hasn't been mentioned, but that's a key factor.
Yeah, and again, that's not a step you can take until you have your plant, but yeah, test beds and scale demonstrations are.
Now, the thing about waste control specialists and energy solutions applied is they have their grouting facilities up and they've been running for a long time. So they know what all the idiosyncrasies are in those plants. They're not in startup mode anymore. And the problems that I just mentioned with a new design, a new plant in startup mode, presumably they've worked through all those years ago. So they don't have to worry about that. And that's one advantage that they have over us if we were to start from scratch and build a grout plant here.
Totally agree.
All right, so the next up, we're rounding back to Matt, and we have Mia, Larry, and Ron. Matt, let's see that.
Well, I got some more chemistry questions since we got our expert there. I really appreciate it. Now, I really enjoyed the one slide where it showed your different grout matrices, where it had the alkali activated cements with the geopolymers and things of that nature. Could you talk a little bit about the differences between saltstone and those alkali activated cements, especially when it comes to the Hanford takes that are going to be a high pH, I guess, in this case, moderate sodium molarity material, and what type of grout would be indicated for that?
Yeah, so this is where you start to cross, where definitions really start to cross over with one another. So first, saltstone is a specific range of formulation, but a specific formulation range approved for use at the Savannah River site. So it's started out a mixture of fly ash, blast furnace slag, and Portland cement, and it is now cement-free saltstone. They've been able to, Christine Langton is the scientist down there who's done decades of great work, where they've moved away because of the cost of using cement and ensuring it, supplies of it. So saltstone is a specific formulation that Savannah River uses to immobilize their low-level salt waste into the saltstone disposal units. Its main components are slag and fly ash. Neither of those are cement, even though the slag that we use here, the majority of it that Lafarge and others supply in the US, is now more classified as a slag cement because it's so reactive. But usually if you're using blast furnace slag or fly ash, you have to alkali activate those because they don't have a, some Class C fly ashes could have enough calcium to drive the reaction, but usually you're going to want to add an alkaline source to kind of kickstart their dissolution faster and get them to hydrate and react. So, and in the geopolymer spaces, we start to take cement out and we look for, if we want to use mixtures that are fly ash, metakaolin, slag primarily based, the waste, if you're doing LAW or PTW, the waste actually brings some benefits to it. So if I'm making a geopolymer for an industrial application, I will take my dry reagents, and usually you have to add in an alkali activator. You have to add in, normally it's potassium hydroxide that's used because potassium helps with that polymerization, but you add in a basic solution to kickstart the reactions to get that material being made. But if you're taking a low activity waste or a pre-treated waste and using it in the reaction, well, it's already bringing that alkalinity with it. It's already bringing some of the components that are involved in those reactions. So you're already a little bit down the road in making a material. So there's been research that's been done at the Vitry Estate Laboratory at Catholic University over the last 4 or 5 years. Wei Ling Gong is a scientist there, where they have demonstrated a wide range of different grout formulations, a lot of things that look traditionally like geopolymers, and their ability to solidify simulated low activity waste. So we have more options in our toolbox when we go to screen things in the future. So from our end, yeah, if you take cement out, I think you're perfectly fine to call your resulting material a geopolymer. There's different classes of geopolymers you don't have to alkali activate, but in our case, if you're using tank waste, it's an alkaline environment, it's going to be alkali activated. So depending on the ratio, there's a lot of terminology you could use of neutral salt activated slags or activated alkali activated slags and what your waste form technically is. But if you want to have a takeaway from it, if there's no cement, you're more than welcome to call it a geopolymer. If you're using a waste, like a simulated tank or an actual tank waste to do it, you're alkaline enough that it's going to be alkaline activated. So hope that was clear.
Yes, and I have just one follow-up. You know, you mentioned some of those newer SCMs like the kaolin. What is the availability of those materials? Are they fairly common in the marketplace now? There wouldn't be supply limitations?
Yes, and so there's been 2 studies that what formerly WRPS had done in my time here of screening material availability against what the mission need would be for various scenarios of treating tank waste. And even though it's a large volume that we have to treat here at the site, relative to how much cement and concrete and cementitious materials we use domestically and in North America and globally, it's a drop in the bucket. So we do have at the Savannah River site, I know they do a lot of, part of the reason of going to the cement-free saltstone, and they do a lot of work of ensuring for continued operations of saltstone that if their slag source changes or their fly ash source changes, that they still make the same product and getting all that documented. For those emerging materials, things like metakaolin, silicate fume are global demand for them is increasing, and they're, so in the case of use metakaolin as the example, it's produced in the same process that you would make cement. So when there was a larger thrust the last 4 years of carbon-friendly cements throughout academia, a lot of folks turned to metakaolin and other clays to just put, because you can calcine them at lower temperature, so your energy demand is less, your CO2 that's generated from the process is less. So there's been a push within the cement industry to make those materials more available and utilize as replacements for cement at a wider stage. And as they continue to become more available, our utilization of them may increase in our likelihood to do it. But today, if you wanted to do a metakaolin based formulation, you could acquire it enough to sustain the annual production rates that we would have here in the mission. So yeah, I don't know if there's one representative here from Works HGC, but the information from those reports made it into the last FFRDC study for the National Academy of Sciences review. The material availability question was placed into, I think, volume 2 of that report. I forget where I'm in. Question.
So, a question for Matt and Ricky. We are at the time we were scheduled to take a break. Would you have a few extra minutes? And stick around and answer some more questions?
I'll stay as long as we.
All right. You're okay with that as well?
I'm good until 4.
Perfect. All right. So Mia, you're up next.
Okay, thank you. I have a few questions related to waste volumes and the expansion factor. So I know that the supplement analysis that was recently released referenced a 2013 PNNL report with a determined expansion factor range from 1.5 to 1.8 for determining the grouted waste volumes. I'm curious if this is the most recent report looking into the expansion factor range, or if there's a more recent report out there.
That's the most recent one that produced data specific to that. I'll give some context to it. The most studied formulation here for use at the Hanford site is called Castone. It's very similar to the original saltstone formulation. Came out of a study that CH2 and Hill did back in 2003. So for that mixture, which is slag, fly ash, and cement, and you're mixing it at a water to binder ratio of 0.4 to 0.6, your volume expansion using that formulation range is about 1.5, 1.8, and that was the formulation that study looked at. Predates me. But we've been making a concerted effort this year with our testing at PNNL to measure and report the volume expansion factors for all the grouts that we're testing, because it is, as we move into a scenario where we could be solidifying and transporting off-site, we want to know what volumes we're producing. So my team in the lab is back on an effort of getting information out of expansion factors on a broader range of grouts. So we don't just have to take the Castone number and extrapolate it out to different formulations. And that includes working with the treatment vendors and the formulations that are used for TBI.
And is this something that you'll then will culminate in a report that's publicly available?
Yes, we're working right now. One of my postdoctoral researchers is working with staff from H2C, putting out we're gonna have a journal article out if he gets working, hopefully in the summer. Then one of the properties we've looked at is the relationship between expansion factor and composition of the waste, because it depends on, the main driver is how much liquid you have, how much solid you're putting into that liquid. You can do an estimate of just based on their densities, what your expansion factor would be, but then your air and train and how the reactions happen, shuffle it a little bit. But yeah, that'll be out, I would hope, by the end of the summer, publicly available in the literature. So.
And
That's
you're
great.
probably not ever going to have a single liquid to solid ratio. You're going to have a range of that. And so you're going to have a range of expansion factors. There's no way around it.
Oh, exactly. And that's what we're trying.
Yeah.
That is one of the main drivers of that is that we've got, it's got a bit of a parabolic shape to it, but we've got a line that says if you're doing this approximate waste chemistry, you're mixing at this ratio, you're going to fall somewhere in this expansion factor range.
Okay, that's great. I think so. I represent Hanford Challenge on the board, and our concern is that these lab studies can't accurately reflect what will actually happen with when grouting Hanford's tank waste. So I'm curious how you can determine an accurate expansion factor based solely on lab studies.
So, two ways to go about it. One is the work we do in the laboratory, when we're testing with our simulated waste. We're doing a lot of the work, developmental work we do is non-rad, then move into the rad space. But the simulants that we do testing with are designed either to represent average ranges that we'd anticipate to receive from the tanks, or working with simulants that are designed to be tank specific. So the last year, obviously to align with the stuff that's going on with TBI, we've made simulants that match up with the SY101 retrieve waste composition. So we can study in the laboratory how our grouts respond with average or different ranges of simulated compositions or tank specific ones. And then the next step to it is when we get opportunistic waste samples into PNNL through our rad waste test platform, which supports WTP, we try to be, if we have an opportunistic chance to maybe produce a small grout sample out of it to ensure that our simulant data matches up with the real stuff, we take that opportunity. And as we continue to move through the mission, what I would hope to see one of PNL's roles continue to be similar to how we support WTP through the test platform, that we have a similar capability established and maintain that as we get specific waste samples from the 200 West area tanks, we can take a small amount of it, evaluate it in the laboratory, and verify what we saw against simulants. And from a chemistry standpoint, if we make a simulant, it's got the same chemicals in there, the same ratios that the actual waste does. If we're dealing with low activity waste or pre-treated waste, you removed the dose that could induce radiolysis and change some of the chemistry. So you're dealing with something that from its fundamentals, it has the same chemical components at similar ratios, you see similar behavior. That's why we have confidence in our simulant work, but it's always good to check against the real stuff when you have it. So that's a nice component, and that's really helped, as an aside, that's really helped the vitrification mission and get the WTP close to start, is our ability to have take samples from the tank farms, move them into PNNL, do demonstration testing through filtration, ion exchange mimicking Tister, put it into a lab scale melter, see how the real stuff compares to what we've simulated in the laboratory. And I would hope that that just keeps continuing, and it's not that difficult financially to keep doing that. So yeah, it's, where does our confidence come from? Chemistry is as similar as we can make it, and we try to verify against waste samples when we get the opportunity.
That's helpful. Thank you. My last question is, when do you see Tech 99, iodine 129, nitrates, nitrites leaching out of the grouted waste form? Like, how many years after grouting do these specific things leach out?
Many variables depending on what the disposal environment is, what the water ingress is. So when we do, and what we've engineered the grout itself to do. So if we take just regular Portland cement, mix it with waste, and it contains technetium, iodine, nitrate, nitrite, all of those species would leach from that waste form at approximately the same rate. They all are anions. Anions don't really interact with cement matrices, so they would all kind of come out at about the same rate. And if you're just in Portland cement, no engineered design to improve retention, what release is dictated on is how porous the material is and how tortuous the pathway for those contaminants to migrate out. So you would see them diffuse at pretty much the rate that's dictated by that porous network. Then if we start to put different additives into it, so if we add in blast furnace slag, for example, blast furnace slag is going to reduce the Tech 99 from technetium 7 down to technetium 4. Technetium 4 is insoluble. It's going to precipitate out in those pore spaces. Be just sitting there. If you leach that sample, the nitrate and nitrite and iodine are still non-binding. You haven't engineered anything into them to slow down leaching, so they will leach out at the rate that's dictated by the physical properties of the material. But the tech release is going to drop off because you've chemically reduced it to an immobile state. So you'll see its release be much slower. If you then put an additive in to bind up the iodine, so we've seen success. It's not a practical solution per se, but if you add a little bit of silver in, silver iodide, very insoluble, precipitates the iodine out. Then if you leach that sample, that's blast furnace slag, contains silver containing additive, Nitrate and nitrite will release at the rate dictated by the physical properties of the material. The iodine and the tech release will be suppressed. Depending on the formulation, those release rates change. Depending on the water content or the rate of water contact with the material, those release rates change. Depending how the pore spaces of the grout evolve with time in its disposal environment, you get precipitation of minerals within the outer pores. If you've got a high carbonate containing solution, that can slow release. There's a lot of variables. There's not just one answer to how fast will they reach out. It's ensuring that we have data to understand how those various contaminants, radionuclides release from our materials, what mechanisms are controlling that release, and that we've got good numerical models that can simulate that release across laboratory tests, representative tests, field tests, and extrapolate it out to disposal timeframes. So.
In Utah and Texas are very dry.
You're
not gonna have much water.
Yeah, and they have their own performance assessments for those sites dictated by their regulators that give inventory limits for what can go into those facilities and what waste class of waste forms can go in. So energy solutions can take class A waste, WCS can take less than, or class D or lower. And yeah, their performance assessments handle it as there's an inventory in the facility. And based on that inventory, there's no pathway to releases. No pathway to potable water, to groundwater. And those PAs are publicly available. There's summaries in the FFRDC study.
Back in our queue, we have Larry, Rob, and Chris. Larry, you're up.
Thank you. I thank you very much for the presentation. I enjoyed it, both the depth and the breadth of your presentation today. I think that maybe you've answered in part, although at different times, most of what I want to ask about. I'm still sensing a disconnect in information. I'm referring to a PNNL study from several years back that analyzed some contents of at least a portion of the tanks and indicated that the formulation of toxics and radioisotopes was variable almost tank by tank. And I'm also aware that contractors that would win a contract to grout some of this waste are for the most part using formulations that are proprietary. The PNNL study indicated that grouts had to be modified for several or many of these tanks, that the only commonality was pH, which was above 7. And I'm wondering how that disconnect between proprietary grout and the need for variability can be met, and whether PNNL has addressed that issue, and whether maybe ecology and EPA would also respond to this, how this would work, rather than just saying, well, it has to meet regulatory compliance when it goes to the waste disposal sites. Can I maybe address that, please?
Yes, so that goes to, that feeds right into what Chris was highlighting earlier, that you have to ensure that you can produce the thing in a facility itself. So without knowing which specific report you're referencing, I'll give 2 examples of where I think that information might have come from. The first one related to the grouting of low activity waste. One of the largest studies of the cast stone formulation was done in collaboration with PNNL and Savannah River between 2011 and 2013. Predates me by a year. But that study screened a matrix of 24 different waste compositions and looking at 2, based on the entire projected supplemental low activity waste viewed at the time, looked at 2 different ranges of sodium molarity of a 5 molar, straight in the tank, 7.8 molar, something that had been evaporated. And then they looked at high and low values of aluminum, sulfur, and phosphate, and highlighting that as you get through the retrieval mission, depending on what sequence you take, what dilution factors are, you're going to see swings in those components. And that study showed that if you use just the cast stone formulation, you do see variation in properties, but these materials were still setting, you were still getting ideal compressive strength. So that report is P&L 22747. Joe Wessick was the main author on it. It was a very thorough evaluation of if you did have variations in chemistry, this one single locked in formulation gets you your desired properties. The other study that comes to mind, which is I'm contemporary with, was related to secondary waste, specifically the brines that will be generated from the effluent treatment facility. Now, the ETF brine, because you get a sulfuric acid treatment for pH control before you feed the waste or the liquid effluents from WTP through the ETF, and then you evaporate all the liquid off, you end up with a concentrated sodium sulfate brine, essentially. And I mentioned this earlier, that sulfate could be a challenge to conventional cement approaches. So there's another collaborative work between us and SRNL where we acknowledge that potential challenge, screened a number of different formulations. And in that work, using cast stone, our most studied formulation, you mix it with that ETF brine, it sets, but very soft. And if you get it to set by pushing the calcium ratio, it'll kind of crack and crumble because there's such high, your calcium to sulfur ratio is completely thrown off. But what we're able to do is look to some commercial formulations, some work that the 222S lab had done, exploratory back in 2007, and then some of our, working back and forth with our collaborators at Savannah River, defined a number of formulations and show that if you add in hydrated lime, therefore getting your calcium to sulfur ratio back in check, you make very good performing waste forms. So I think to go to your question, those are the two reports that I think you could be referring to. And in both cases, identified that yes, you could have changing chemistry in the tank waste. In our secondary liquid waste that we handle, you could have some challenging liquid chemistry, but you can formulate around it. And on the waste side of things, as we get better definition of what the retrieved waste profile will look like in 200 West area, we'll work hand in hand with the contractor to ensure we have data that shows that these proprietary formulations are able to solidify the waste so the vendors know ahead of time. That's why we have NDAs with the disposal vendors, so we can work hand in hand and get knowledge of what those proprietary formulations are and kind of give a heads up in advance of what changes in waste chemistry, what impacts those could have on those formulations. That's some stuff we're doing right now for them. So, and if you remember or you want to follow up after what the specific report was, but those are the two that come to mind where we identified changes in waste chemistry and how the Grout responds to it.
Thank you.
So,
This is Michelle from EPA. I'll just say for the TBI tank waste, we weren't really concerned that the grout wouldn't be able to stabilize any of the chemicals in that particular tank supernate. But where your point about the remaining tanks being very variable in content is one we're aware of, and there's no designed plan for how the future variances or variants will be issued, whether it'll just be one for the rest of West area or one per tank or anything else. Hasn't been decided yet, and that'll really be up to DOE and how they decide to apply and petition EPA. But certainly when we evaluate the information for the purpose of issuing the variance, we will be looking at the individual tank chemistries. And if the grout cannot be demonstrated, to be effective beforehand, perhaps because of the confidential nature of the recipe, etc., we may end up requiring some kind of pre-treatment of the tank waste that wasn't necessary for SY 101, but may be necessary for different chemistries of future tanks. So, you know, those are discussions yet to be had, but I guess I just wanted to say that EPA will definitely be looking at the chemistry of the waste that's in the petitions and using that as the basis of our evaluation as to whether the variance petition as written is approvable.
Thank you.
I'm not sure we'd add much more today for our side beyond some of what Michelle covered, and I imagine we'll be working closely with DOE and EPA on some of those questions instead of moving forward, on the ecology kind of side of things, to what Michelle was speaking to.
I'll give the final questions.
Yeah, okay. We go on and on and on, couldn't we? So just a clarification for ecology, she talks about it being high-level waste tank. She realizes it's processed high-level waste. It's the liquid, it's the water, it's coming out of Tisker. Okay, it's not the high-level waste, anyway. So one of the things we did back in the 70s with Rockwell, and there was some P&L guys. I remember Koenigs, Dr. Koenigs was a big one in leaching, and some of the work that we had performed for was to note that there's about 23 different kinds of additives you can add to cements and concrete to improve their properties, adjust this and that, including several mechanical methods. So one of the things that the Koenigs and Battelle did at the beginning is the porosity was a key factor in the transport of anything away, leaching the products, et cetera. And you mentioned tortuosity here at the property. The mechanical vibration is a very common tool, or ultrasonic vibration, a common tool to reduce the porosity in cementatious structures. And I would think that if we run into several problems there, that should be kind of highlighted as being one of the things that we're really interested in is attacking the mechanism for which the release occurs, and yeah, we're immobilizing it, and we're recognizing there may be release over centuries or whatever. But if we would take those mechanical steps, and so I'd like some understanding, are you standardizing these, or are you setting in your procedures for making the grout some sort of porosity reduction or chemically treating it?
Yeah, and that's a target of a number of the formulations we're trying with us, VSL Spend are trying to mature and get into our toolbox. I will know one of the things that we do when we fabricate laboratory samples is we use mechanical vibration to just ensure we don't have any excess air entrainment. And that's just based on the way that we mix versus would mix in a facility. So we'll put it on a vibratory shaker or some hard taps so you see bubbles coming out. So doing that mechanical vibration helps you lose entrained air. If you do too much of it, you can get segregation, which you don't want to do. If you're not at a far enough point in your hydration reactions, you can actually segregate your particles down. But for us, we always do it to avoid there being large air pockets that would skew our results. We take more of a formulation approach to reducing porosity. One of the additives that I mentioned, silica fume, or adding silica flour in, the whole purpose of that, very fine particulate reacts slowly. So as you form your pore network, the silica fume particles exist in there, then they react and they kind of fill that pore space. When Dan was running through his comments, he mentioned the ultra high performance cement composites, something that's we've pulled out of industry applications in the precast field into our application because their goal is getting very high strength by going to low water content. Low water content equals lower porosity. You put some fillers in there, you get even lower porosity. So that concept of what has now become termed the ultra high performance grout for the screening test in the laboratory, the whole purpose of that is low water content, low porosity, low permeability to water, therefore much lower release. So we take steps in the laboratory to ensure don't have those artificial things. But the more beneficial route on our end, and from my view, is doing it from a formulation standpoint, more so than the mechanical methods, because you get physical filling, but.
Right, right. All right, well, I want to thank you a whole lot for coming in and talking with us. You have another question? Okay, Chris? Okay.
Ricky, this is for you. When Energy Solutions Waste Control Specialists grout the waste, how do they dispose of it? Do they just take that grout and dump it in the trench, or do they put it in some kind of cask and then store the cask? Because they put it in the cask, and the cask is thick stainless steel or something like that, bleachability and pathways to groundwater are totally irrelevant. That waste is gonna stay in the cask, ain't gonna get out, and no components are gonna get out. But if they just dump it into the ground in a trench, then that's a different story. And how are they disposing of it at your sites?
Can I get back to you on that?
Okay. Well, I think that's,
Unless you know.
yeah, I think that's kind of a key consideration.
So they do have different methods. It's not within a steel can. The FFRDC study, the National Academies one, he gave good publicly available descriptions of what each one would do. WCS goes into, they've got their individual cells, the material will be directly loaded into, or sorry, Energy Solutions has their cells that they'll just directly load the material into. WCS has more vault-like structures where the forms get placed into the vaults. So their products, their final products are suitable for what their disposal configuration is.
So they're putting them in engineered cells.
They have an engineered, yes. Both facilities have engineered cells that have different construction mechanisms for how the waste is received into them.
And I'm only asking to provide a response at a later date because we're working with the vendors to provide kind of better communication tools, kind of graphics and visuals to help with this, and I just don't have that today.
Could there be optimization of the volume that you could route at one time? In other words, we'd be shipping thousands and thousands of gallons.
I think we'll work with the vendors as we get closer to production.
Okay.
Yeah.
Would you think that there would be a size limitation on grouting?
We have the limitation on the capacity of the facilities.
No, I meant, larger size of the casting, more internal heat, more breakdown. Would you have?
And it depends on the formulation you're using, with, again, if you, a quick work around that. So as you scale up from like a 55-gallon drum to a V25 box, to a roll-off box, to a large vault, you have different heat control mechanisms. But if you play with your reagents a little bit, back off the amount of cement, you get that heat generation down. And really, the heat generation at those more like individual unit handling sizes, fairly comparable to one another. It's when you scale up to a vault that formulations and the heat generation rates start to impact things.
Yeah, like the tons.
Yeah.
Yeah, that was
what they do. Yeah. Not as much of a big concern.
We're driving out there and seeing steam come out these holes. Thanks a lot, if that's the last question.
Oh, thank you.
Yeah, great job there.
Thank you both. I think you're free for the rest of the day. We're getting out of here by 4. Now you're glad with full 2 minutes to spare. Yeah, thanks.
Oh, me. It's like, okay.
Yeah.
Makes hard rock.
Like how long until it's
Second, you shuffle out. Rob,
a couple months?
how would you like to prioritize your last half an hour?
So they're still saying goodbye.
Yeah.
Yeah, let's think.
I think you're still in bicycle.
You guys want to take any side conversations outside?
Oh, sure.
Thanks. Sorry, not trying to be.
Oh,
Yeah.
You know a little bit about cement.
Yeah. 5 minutes.
It's a couple of people here. They asked the question, what did you learn?
It's almost, that's all it's pretty.
Hey, Chris, if you guys want to take that outside, it's still going on.
Thanks, Matt. Well, on our schedule here, we're supposed to ask ourselves if we have any good reflections or reflections of this meeting. And I guess we got more people online than in the room. So, what are we gonna do about this?
You're free.
Round table?
That too.
Sure, let's do it. Who wants to start?
So the question is, what did you learn today and what else do you want to know? We're doing a round table. We can take volunteers from anyone online or in the room that'd like to contribute.
Josh, I think, are we not taking a break? I think people just left, right? Or are they just leaving?
We have a half hour, so we're just prioritizing.
Got it.
I got a quick question for Brian for ecology relative to this last discussion. What was the properties of this liquid that was trucked out of here? And how did it get from here to Utah and Texas?
That's a great Ricky Bang question. I think the presentation slides that Ricky presented kind of showed the, and you can see the materials after the fact, that they kind of showed the trucks that they went on and the containers that they were in. So I think Ricky's presentation honestly did a pretty good job talking about kind of the waste and the shipment. It's not something I can speak to and accurately on that. That's better for energy.
Yeah.
We've been told that they ship the containers back again for food they used.
And the Tisker, well, so what it did, they have, the ion exchange, the CST, and so it produces really clear liquid and that, low solids. And when they, measured, I understand that when they looked for settling, once they got to their destination, they didn't notice any extra settling. So that's, so, it's like clear water almost, very low radiation.
Dan still has offered a comment on the round table. Dan, you're up.
Well, more of a question than a comment as far as the radioactivity of the 2,000 gallons was shipped. How does it compare to normal occurring radioactivity that's shipped all the time from fracking and that sort of thing? The norm.
Our experts are gone.
I recall
Well,
there's a
EPA
data sheet. I recall there's a TBI data sheet out there with some discussion about that. I don't have that real handy, but the data sheet, the DOE data sheets.
Tell me by chance.
I think I found it. I'm gonna put it in the, I think it's the Department of Energy fact sheet that you're referring to.
Yeah.
I think I know what you're talking about.
Well, does it compare to norm?
Well, they said that the shipping out, they were contact handled. So in other words, they loaded them on the trucks, contact handled, so it wasn't that severe.
Yeah, I
I
understand
can't
that. I'm just trying to get a sense of the relative dangers of shipping norm, which is done all the time, and then shipping this stuff in liquid form.
Well, if I may interject, I would say that this material, those containers were well engineered for this type of an event. It was a limited quantity, so that doesn't quite compare to norm that has a lot more quantity. And usually, norm is solid, whereas this was liquid. And if what Ricky said today is true, at 0.5 MR per hour, that kind of compares to a cross nation flight, I believe, is cited as 0.2 MR for a cross nation flight. So, the dose rate, well, what I would call higher than background, wasn't too bad, unless you had a specific amount of norm, it'd be very hard to compare them.
Well, just two similar truckloads.
Yeah. So, yeah, until I get that data, I wouldn't be able to compare it either. That might be a DOE question.
Okay. All righty. Thank you.
Does fit in with what else do you want to know after that round table?
Since I'm already talking, I was curious to find out, obviously, I have a chemistry background, so I really, I enjoyed that part. I was also, what Ricky said mirrors a lot of the other presentations we've had about TBI, which is relieving. I like to see that. I think what I'd like to see in the future, there was some discussion about, well, why don't we ship this off-site to Grout facilities, because those facilities already exist. I will say the most recent SA5 supplemental analysis doesn't necessarily support that the facilities exist now that can grout all the potential material. So I would like to see something like that, a system volume, perhaps, our potential range of volumes and potential range that these facilities could take. And also there's, when you're talking about just 200 West in this volume, there's a lot more tanks out there. And a lot more uses for grout on site, should that be chosen as a way to proceed. And it'd be interesting to know a potential volume range of material on site that may qualify for grouting, assuming it's past a weir and such.
I believe it said 32 million gallons.
Yes, that's for the supplemental analysis for just 200 West. That's there. But when you start looking at other system plans and some of the the life cycle reports, that volume starts going up. And so then it makes it a different calculation, the value of putting a grouting or batch plant at Hanford, especially when you're having more processes than just the 200 West that could potentially be grouted.
Next, I'd like from Mia and then Chris.
Yeah, this was a really technical conversation and presentation. And a lot of it I just didn't understand or didn't get. I think it was really heavy on chemistry and what goes into the grout without, my interest is more in how is this all going to work specific to Hanford and tank waste. So it would be nice to have a presentation that's more specific to that, and more time for just open discussion and Q&A. I had additional questions that we just ran out of time and I couldn't ask them all. So maybe, sending those to Megan and having someone come in who could do less of a technical conversation, but can speak to all of these things would be helpful from my perspective.
Yeah, I would recommend if you guys have unanswered questions, Rob, you as chair, if they can send them to you and you can consolidate and then send them to us. We can get them to the SMEs and then look at having it at a future, whether it's full board or just subcommittee meeting, and having more of a discussion and less of a presentation.
Yeah, I'll be glad to do that.
Yeah.
Thank you.
And go ahead, Chris.
I'd just like to say something about variations in tank chemistry and number of grout recipes you might have to have. The same thing applies for vitrification. In the vit plant, they have a human-machine interface, and that human-machine interface basically is programmed to give a number of vitrification recipes, that is, a number of different types of an amount of additives you have to vitrify a given waste coming from a given tank. They need some input, and that input goes into the human machine interface, and then automatically that dumps the different kinds and amounts of chemicals to create a slurry that is then vitrified. Grouting is the same way. There's no difference between what's going to happen in vitrification here with the variations in tank waste and the different amounts and types of glass forming chemicals that have to be added than you would in grouting. Exactly analysis. If we build a grout plant here, we'll have a human machine interface and we'll have some inputs coming in from the tank waste, and that will automate the recipe. Those recipes, a range of recipes will be done by treatability studies, but there'll probably be very few of them because a grout recipe is surprisingly robust for a wide range of waste chemistries. The concern that we had at Fernald was not that something wouldn't set up or cure, but that it would set up and cure in the mixer and we'd never get it out. The cementation process and the curing and the hardening was that fast. We were worrying about it solidifying in our mixers. And we had to make sure it was liquid enough to get in the cask and self-leveling in the cask. But the thing is in today's world and where things stand, and with the advent of computer control systems and human machine interfaces, varying grout recipes as a function of different waste, whether they're vitrification or grout, is not a big deal. It's almost a given in the industry these days. And I imagine that waste control specialist and energy solutions at Clive have exactly those same things. They have human machine interfaces that they can vary the additives for a given waste type just with simple knowledge of what some of the characteristics of that waste are.
And
I thought the presentations were outstanding, and I'm not a chemist or an engineer, but I think they provided information to demonstrate the analysis that's been done, how things are going to work, how they're going to deal with variations, to give me great confidence. And I just thought it was great. And I think the Hab is getting awfully technical. So we're not chemists, we're not engineers. And those of you that are need to have your own conversations with the people that can answer your questions. And then if you see a problem, come back and tell us and we'll look into it. But we're up here, guys. Anyway, it was great. I'm really glad that we had this. Thank you.
anyone else with any contributions to the roundtable?
Now, anybody online that wants to make a comment? So then, I expect that, we've been asked to generate some sort of advice on grout for the Hanford site. And it's been for a couple of years, and we now have this presentation. And we're gonna get probably that same expectation again in our work plan coming up. There could be several avenues for advice. Advice saying more caution, advice saying, go full speed ahead, so. Excuse me. So any ideas that you might have on any particularities in the advice that you want? I think we're kind of getting hung up on the fact that these sites here have what they call proprietary blends. But really, there's no magic to their proprietary blends. There's only so many constituents they can put in there. And because the P&L has the NDA, the non-disclosure agreement with both sites, I'm more worried about if we send a batch of groutable water down to one of these sites, is that how the specification is planned for that particular waste. And I know that when we're building like WTP, we have an interface control document where the specification for what that liquid's going to be is written down, and it has to meet that or it's rejected. And so, that's the reason why I asked several times about the specifications. Because I know that that's quality assurance, you know, if you meet the specification, meet what you're doing. So how do we perform quality assurance on Grout? Is really probably my big question. And how is that done? Because if we've got good quality assurance and we've got it, that means that all the boxes have been clicked, and all the things, and I can feel safe and comfortable with that. So,
If we send stuff to be grouted off-site in liquid form, let's say by one of these, we're gonna have to write a procurement. We're not just gonna give them money. There's gonna have to be a procurement and there's gonna have to be specifications. So maybe what we could do is we could advise DOE on some key things that the public or the HAB might be concerned about that they need to put in a procurement. That'd be policy level. We're not getting down in the weeds. We're saying that, hey, they have to, the police control specialist, for example, has to demonstrate to DOE that the Grout meets certain characteristics. And they don't have to be hardcore technical characteristics. But I think whatever happens is DOE is gonna have to specify in a procurement. They're gonna have to put specifications that these people are gonna have to meet. And maybe the advice is we could advise DOE on these things and keep it generic, sort of generic quality assurance, quality control things. To put in the procurement that would go a long way towards satisfying, you know, the public. We're certainly not gonna send 32 million gallons somewhere without a pretty lengthy procurement and a procurement process. And they're gonna have to write proposals that are gonna have to be evaluated. And we could say the proposals have to address these things.
I think sounds a good idea. Okay,
Nash has some closing thoughts on that.
yeah, man.
Oh, no, I think Chris had a great idea, but also I know some of us aren't privy to next year's work plan yet. And I've been hearing that there's going to be quite a bit more advice documents asked for by DOE from HAB. So if you're attending the leadership tomorrow, Rob, you know, getting the tank waste focused asks in front of us as quick as possible. That way we can start, you know, setting up our IM groups. That would also help.
Sounds good. Thanks, man. Okay, the next one is the real tricky one. I nominate Chris Sun to be the vice chair. Chris, do you want to say something?
Yes, sir.
Sure.
So,
We'd like to do it again.
Close nominations.
Yes.
Second.
so we're looking at Quist leadership nominations. We have one nominee for chair, that's Rob Davis, and one nominee for vice chair, that's Chris Sutton. We have heard a second for these nominations. Is there anybody else that'd be interested in self-nominating or nominating another?
Somebody else.
I hear silence, which means support. Okay, spell check. Is everyone in favor of Rob continuing to serve as TWST chair?
You want raised hands or voice?
How many don't?
Yeah, I can check it.
That's what we did yesterday. Was anybody not in favor of Tom?
Yeah. Congratulations, sir.
Okay, well, so we checked for Rob, just to confirm. Is anyone not in support of Chris continuing to serve as vice chair? That is a celebratory silence. Congratulations to both of you.
Yeah.
Who said that?
I don't know. Have you heard of the screaming goat? Oh, it's.
So, lightning rounding the remainder of this, you know, we've heard the leadership workshop spiel. you know, work plans coming, is there anything else you need to seek input on from this committee leading up to that?
We'll find out
So,
tomorrow.
Yeah, we'll find out, yeah. Now, we're all in this room.
In this room, yes.
We all gonna fit in here.
I counted chairs based on who I believed was coming and I concluded yes.
Okay.
And I'll double check that after. we clear out.
So Brian's coming, right?
Yes.
Brian Bell? No.
No. Our kids.
I forgot. Thinking for September, do we have any ideas of what might be right from the agencies at that point?
I think if you guys get your questions to Rob on what you didn't get answered today, then we could look at possibly doing like a discussion on your questions from today. If you want to.
Sounds good.
But also I think it is an opportunity to look at discussing, unless we do it at August full board. Like what opportunities or what meetings you guys would like, what discussions for you guys.
Yeah, I think that, there's this idea of looking at it from the perspective of what you put in the performance specification. I think with that, that's probably a decent idea.
You know, I think a presentation that would be really helpful. And at least in the 5 years that I've been on the HAB, we've never had a presentation like this. Would be, what are the DOT, Department of Transportation, and NRC Nuclear Regulatory Commission requirements for shipping and transporting radioactive waste? They're extremely rigorous, they're complex, and they address a lot of the things that we've kind of been batting around. They address the amount of radioactivity, they address the type of containers, they address who has to approve the shipment, so on and so forth. And I think that would be a pretty beneficial discussion to have, because I know personal experience working on site that nothing can be shipped off this site without approval by a certified shipper. And we have a department of certified shippers on site that have extensive training and DOT regulations. And we ship radioactive waste in different forms off the site all the time. And they have to be approved and meet DOT regulations. So I think that'd be a really handy presentation to have sometime in the future. Because there's a lot of concern about shipping, liquids, radioactive liquids off-site. And so I think if everybody knew a little bit more about the DOT regs on this, at least it would give a lot of information that I think would benefit future discussion.
September, we're thinking potential follow-up on Grout discussions to seek unanswered questions or seek answers to unanswered questions. And potentially thinking about future advice and path forward on those. See what presentations, if any, are available and timely. Final lightning round.
And then we also are gonna end up having our tour of the amps, correct?
Yeah.
That's during the orientation, or is it? What did we decide on that? Because
I was trying to find, you'll have to excuse me because I don't have the background knowledge on all of it, right? I found a couple of emails that were kind of making it sound like you guys are like able to go whenever you want.
this is a thing that, Eventech is managed, anyway, they have been commissioned to do the amps. And, through friendships that we've had over the years, Rob Hastings, I said, come on down, get a tour of this thing.
Yeah.
And so I went down and sure enough, it's a really nice setup. They're mocking it up so that actually the workers can see what they gotta do to work around. And, he said, yeah, after meeting, you guys bring everybody down, we'll just go see it, okay? Well, then we were told by the DDFO that we shouldn't do that. And they want to save it for some other thing. Well, I'm concerned that they're gonna tear the mock-up down because it's in a building, they're renting space for it, and I felt that, you know, we just basically got told, you know, that DOE will arrange it for us. Because you want everybody to go down there. So, so I don't know, you know, I'd really like this group to go down there and see what they're doing and listen to their discussion and get an idea of just how clean that water can be made. And know that they're adding an extra filter to the next amp set, so it's gonna be 4 of those big containers. And, so I just basically stayed away from it and haven't called Rob. I did want to call him the other day and ask him about a report, but, if you haven't talked to him, or them, I would encourage you to, and I can give you his phone number or email.
Yeah, if you just want to email to me when you get, I'm separate from when you get all those other things, but, yeah, we'll look into it and see what we can do.
So it seems like at the end of the meeting, you adjourn to this address and people just drive there.
That's what we were planning.
Yeah, because isn't it right here in town?
Yes.
Yeah, yeah.
And I don't think we need DOE's approval to do that. It's like, Mother, may I?
Oh, I know, but the thing was, is I'm risk adverse. I mean, I don't want to create a condition for DOE that, would then embarrass us. Okay, if that we learned something there that DOE doesn't know, then I don't know what to do with it. And,
Well, you might anyway if you went on your own, so
well, yeah,
I just don't think it's that complicated.
I didn't begin with.
Yeah, I can, follow up and let you know, maybe try and get at least a little more information by tomorrow. It is 4:30, so I don't know how much we'll get, but.
You want to write down his numbers and his email. And I would hope that you can give him a call and maybe say, you know, use my name, say Rob Davis has sent me to talk to you about arranging a tour of this. And
you just want, TWST to go, or do you want it to be open to all?
it doesn't matter. Twist.
Hey, Megan, we had something.
I was just gonna kind of recap the last conversation of that as I understood it. The initial plan was, you know, you can go whenever you want, but then the travel restrictions impacted those plans. Whereas a lot of people that would have been coming to the TWST meeting normally were unable to, and that would have significantly impacted the attendance. So during the April meeting, Jen suggested, okay, we want as many people to see as possible. If we group it with the orientation tour, that is our best chance to get everybody on the end to see it.
But we need to make sure it's still standing by then.
Right.
And
If it's not, then we need another path.
yeah, yeah. Thank you.
You guys will have to bear with me as we go, because I don't have knowledge past 8 months ago for a lot of things, so.
You didn't do the Vulcan party well.
Are we done?
Question, a minute and a half left. Any other-
I want to talk for another hour and a half. No, I'm good. I can't see of any other thing that we gotta talk about right now. I want to thank everybody for sharing. This has been really good. I'm glad we got Matt. I'm really glad you guys got Matt. And I don't know why we couldn't get him last year when we'd asked for the presentations, but it didn't happen. So, yeah.
So there is a gathering at 6 o'clock at the social. Because there's people coming into town for the leadership retreat tomorrow. The social is at 7:02 in the Richland Parkway. So if anybody wants to come and join us, y'all come.
What's the name of the place?
It's called The Social.
The social.
It's right across the walkway from Frost Me Sweet.
Oh, I know what that's.
And
Didn't try to run more. Frost Me Sweet, the cupcake place.
if you're planning on going, Tom has asked that you give him a heads up so he reserves enough space for everyone that's.
I think he's on his way here.
Okay, well, so you may see it before he walks in at least.
I'll be there.
So are we ready to adjourn?
Yes, we are.
All right, we're adjourned. Thank you, everybody.
Yeah.